Oh, hi everyone. We will start in a few minutes. I already had one stream this morning on mathematical finance. Hi Scratchbox. I had one stream this morning.
Oh, hi everyone.
What's going on? Why
We will start in a few minutes.
why do I hear myself?
I already had one stream this morning on mathematical finance.
Yeah, how do I?
Hi Scratchbox.
Yeah, what do I do?
I had one stream this morning.
Oh, hi everyone.
Like,
I can
what's
hear
going on?
myself.
We will start in a few minutes.
Why do I hear myself? Oh, because I opened my
I already had.
That's why. Okay. Okay, now we're good. So yeah, so this morning we reviewed basic probability, as well as we started the CAPM model, the capital asset pricing model, and in particular, a first glimpse of the so-called Markovich efficiency frontier. So this is a Nobel Prize winning work on risk diversification, risk management, aka diversification. I don't know if I'll ever get the chance of returning to this topic in near future. I said near future because I have a feeling that we will come back to that, because a lot of people following the channel are interested in this subject. But basically, my hand's a little bit full right now. I have upload duties. Speaking of which, I haven't yet uploaded a video. My apologies for that this week. But we've been having fun on live streams. For example, the measure theory stream is going pretty well, as well as this one, the mathematical statistics and ballistics. A weird combo, but this is what you subscribe for. So, yeah, basically, that's the Sunday stream, which we're doing it on Saturday today because this Sunday I have commitments in the evening, so I can't do it on Sunday. So today I actually am having two streams, which is going to be well over 8 hours. Big day for me. So without further ado, let's just get into today's stream, tonight's stream on mathematical statistics and ballistics. As I mentioned multiple times in the previous Sunday streams, the reason I put these two subjects together is not just because of the technical side of things, but rather to drive home an important point, in my opinion, which is the moral accountability of scientists. Why is that? Hi. Why do we? Why do we? No, why do I? I mean, why do I? I'm pretty sure there are other people who care about this. Is because I think applied mathematics or mathematical subjects that are currently widely applied needs to face its own history in an honest manner. A lot of the mathematical subjects, applied mathematical subjects that we learn today, like things like differential equations, numerical analysis, and whatnot, calculus of variation, and includes the subject for the next Saturday stream, optimal control. They were developed, invented, and used. They were first of all funded, developed, and used by states and military. A lot of mathematicians nowadays warned about the weaponization of mathematics, which I agree with the sentiment. But if we take an honest look at mathematics, it's not weaponization that we should worry about. It's because most of the mathematics were first sponsored and invented by state and military power, and also corporate power. Right? So this is an undeniable fact. A lot of the numerical methods that we learn today
were not weren't just helping ballistics. They were invented. They were born because of it, right? And of course, exterior ballistics was a subject that modern applied mathematicians tend to avoid because the moral implication is gray, because its primary purpose was to increase the efficiency of violence. Right. So for that reason, the author of the book on exterior ballistic, McShane, Kelly, and Reno, said so in the preface, that they wish this book to be useless. The author of this scientific book typically would hope that the book will turn out to be useful. The authors of this book wish devoutly that this turn out to be quite useless. And the applications of exterior ballistics with lethal intent may cease. Okay, so you can feel the unease in the author's tone. But why do we put mathematical statistics side by side with exterior ballistics? Because mathematical statistics as a subject was invented to support the subject called eugenics. So eugenics and mathematical statistics were fundamentally intertwined. They're especially in their since it's in its genesis. Okay, exterior ballistics, not exterior, mathematical statistics and eugenics were highly intertwined. And of course, eugenics was now a discredited subject. Right? Its main purpose was to quote unquote improve human breeding, and it has a lot of the human rights abuses and outright atrocities in the 20th century, culminated in Nazi Germany. Of course, Nazi Germany was not the birthplace of eugenics, but rather England, the UK. And three of the mathematical statisticians, whose work are taught in every introductory statistics course, first course in statistics, were devout eugenicists. So they are Francis Galton. Francis Galton invented the term eugenics. Okay, and if you've taken a course on stochastic process, you probably heard of something called the branching process. So Francis Galton pretty much invented a modern regression analysis. Carl Pearson invented the notions such as a correlation coefficient. Right, nowadays we call the correlation coefficient rho, Pearson's correlation coefficient. And also things like Pearson's goodness of fit test, a chi-square test, widely used for testing goodness of fit, independence, that sort of thing. And also principal component analysis, absolutely fundamental stuff in mathematical statistics. And of course, Ronald A. Fisher. Ronald A. Fisher is considered the father of modern statistics. He invented the maximum likelihood paradigm, which we will look at today. These three fellows were pioneers of eugenics, and in particular, some of them have quite explicit racist and colonialist quotes, which I will not repeat on the channel. And by the way, this paper, I shared it on my Discord server. It's called Teaching the Difficult Past of Statistics to Improve the Future. Okay, so it is in my opinion that modern applied mathematics and statistics curricula tend to perhaps intentionally or inadvertently sanitize this difficult history. But I think it is perhaps wild Stadler, I know, but perhaps my opinion is to my approach. Okay, my advocation is to face these difficulties head on, not just academically but morally. Okay, because applied mathematics and statistics are instruments of tremendous power, and with great power comes with great responsibility. As practitioners, we cannot just say, oh, this is just math, and I just do math, and the moral responsibility lies solely with the client. No. If you develop something, you have a stake in it, and you have a stake in its implication in the real world, and that's my point of view. Okay, so without further lecturing on this field, because you can read it yourself as the paper, I'm just going to put forth my 4-point manual. Okay, and I welcome further discussion as well as debate. So this is Ming's 4-step manual of moral accountability of scientists, including mathematicians and statisticians. Okay, and we'll take this as a nobody's talking about anything seemed dirty. Tesla was in love with a pigeon, and he fat people in the literal sense of the word hate. All right, uh, so these are the 4 steps. First, so as a scientist, what, in my opinion, should engage with their field. First is to have a set of values. Okay, so we're kind of doing it in an axiomatic approach. Your set of values is your axioms. Second, make an honest examination of the genealogy of your field of practice. Genealogy, what do we mean by genealogy? And not just history, okay? Genealogy. How it is funded, who funded it, how it is funded, developed, and used. That's the second. The third one is to, how should I put this? The third one is to reflect the real world implication, not just applications. Of the work, of your own work and your colleagues' work, of the work of the work of your own and your colleague. Okay, and let's put a qualification into, okay, as much as possible. I know the subject of genealogy is difficult. As much as possible. It can be as easy as searching for the top donor of a particular university. Okay, so for example, you can search who donated to MIT the most, and nothing against MIT. Okay, just for an example. Okay, so that's the third one. Fourth one, perhaps it's the shortest, is when your heart screams no, speak up. Okay, So that's the first 15 minutes of the stream. And let's get on with the main subject, mathematical statistics. So last time we were at likelihood. Okay, so we were talking about the likelihood function last time. Let's review the main takeaways. Okay, so likelihood function, numerically speaking, is defined as the probability function for discrete probability models, and is defined as the density function for continuous probability models. That being said, likelihood is fundamentally different with probability or probability density. So likelihood and probability functions, probability density functions are fundamentally different. Why is that? Because likelihood isn't probability or probability density. Likelihood function takes the parameter as its argument. We write L of theta given S, where S is the data. Okay, S is the data. It can be 1 point or many points. It doesn't matter. Okay, but in the main difference between likelihood and probability functions is that in a probability function, the parameter is considered fixed. Like the binomial distribution, like in the binomial distribution, P is fixed. And the values that the binomial distribution can take, such as 0, 1, all the way to n, are the variable in the probability function. But here, in a likelihood function, the data is fixed, whereas theta is the variable. Okay, that's the first difference. Second difference is likelihood function is not uniquely defined. Okay, it's not uniquely defined because the values of likelihood L, the absolute value of likelihood L, does not matter. What we care about is the relative magnitude. Because likelihood function is essentially a ranking system on the parameter space. Its relative magnitude tells us the preferability, okay, the preferability of the parameter, how well a parameter value explains the observed data. So therefore, you can multiply a likelihood function by a constant, and the magnitude, the relative magnitude, stays the same. This way, so we can clearly see the probability you cannot do so. So in the likelihood function, only the relative size matter. And likelihood function, fundamentally speaking, is just a function that you rank the preferability on values in the parameter space. And this is something that I made a comparison with a notion in economics called the utility function. In utility function, economists tend to use the metaphor that says the utility function measures the amount of happiness that a consumer gets from a bundle of goods. But of course, this raises question like, how do you even measure things like happiness? Right? The real answer is such things don't actually exist. But consumers do have preferences, of one bundle of goods over the other. So the utility function is a ranking system on the set of possible goods. A higher utility means a more preferable bundle. Here we're essentially doing exactly the same thing in mathematical statistics. So likelihood function is one way, but not the only way, to rank the preferability of parameter values. Higher the likelihood, the more preferable, in the sense that it explains the observed data better. Okay, so that's a likelihood function, and we see a few examples, including the normal example. Factor analysis. Factor analysis is a topic in multivariate analysis to measure a latent variable. There's no latent variable here. For latent variable, you mean there's something that is not observed, right? I know I'm online twice a day. Today is very special. It's supposed to be on Sunday, but I can't do it on Sunday today. Okay, so Christian, so latent variables models, of course, are hugely important. And you typically, you can also use maximum likelihood to fit models with latent variables. But just dropping, you were talking about measuring happiness. Oh, I was talking about measuring happiness because I was using analogy. I was using analogy that is utility function in economics, in consumer theory, and how that's used to rank consumer bundles, and comparing that with the likelihood function. The likelihood function is essentially a comparing mechanism between different parameters value. So if a function, if a parameter theta 1 has a higher likelihood than theta 2, then we consider theta 1 to be preferable. When we're getting a reading Wittgenstein string, I heard you mention one of your older videos, just curious how you dip your toe into philosophy. Well, of course, this is a side tangent, but of course, I'm interested in philosophy, but I'm not very interested in the philosophy of mathematics. It sounds like a extremely odd thing to say because it's a math channel. Because I just found the typical debate or expositions on the philosophy of mathematics to be very, at least they're uninteresting to me. Like math is discovered or math is invented, that sort of thing. I just find that to be extremely boring. I'm not so interested in that sort of thing. And of course, Wittgenstein is instrumental in one schools of the philosophy of mathematics, right? So Wittgenstein was pretty much anti-Cantorian. You can maybe you can call it that way, right? So in terms of the foundations of mathematics, I personally cannot make too much comment because I don't have a very extensive background in logic, right? So I just find the debate in mathematical in the philosophy of mathematics to be very dry. I personally cannot spend over an hour reading that. Okay. However, I am interested in perhaps something that is not widely discussed in either mathematics and philosophy. That is, what does doing mathematics do to a person? What is the relationship between a mathematician and his work? So that sort of thing. It is more existential. Okay, you might call it the existentialism for mathematics. So that's what I'm interested in. What does doing mathematics do a person's soul? Okay, so we might call it that way. But perhaps that's a topic for a different video or stream. Okay, but here we are talking about likelihood function. Let's take a look at another example, and let's take a look at the notion of, and we'll look at the notion of sufficient statistics. Okay, so this is a hugely important topic because sufficient statistics is arguably the ancestor of modern dimensionality reduction. Okay, example 6.1.5, multinomial models. Okay, so in the earlier part of the book, you can get into that. We will do a quick review. Example 2.8.5, we introduce multinomial distribution. So this is a direct generalization of the binomial distribution. If binomial distribution is about tossing coins, then multinomial distributions are about tossing dice. They arise in application when we have a categorical response. Categorical response variable is S that can take finite number of k values. Like Amazon review, you can put how many stars, like 5 stars, in total of 5 stars. So sometimes the categorical response variable has an order, in natural order between them, like Amazon review, right? 1 star is less than 2 star and whatnot. Okay. Sometimes the categorical responses do not have a natural order. Right? So like age groups. Well, age group perhaps have a natural order because you can order them using age, but like countries of origin, that's categorical. Okay, so that's a natural setting for for multinomial models where you have categorical responses. So the the k values are the possible response, 1 to all the way to k. And here you have, say, just have one data point. And let's say you just have one data point. P of Si equals theta I. Theta I is the probability of S equals I, where I is a value between 1 to k. Suppose then that k equals 3 and we do not know the value of theta 1, theta 2, theta 3. In this case, the parameter space given by big omega is as such. So you can think of big omega as a simplex. Big omega has 3 axes, theta 1, theta 2, theta 3. And the sum of them is 1. So they lie in the plane. And in the first octus, right? I don't know how do you call this. So basically, the part of the 3D space where all coordinates are positive. Sum of theta equals 1. So there's a constraint in them. You don't. You only have 2 degrees of freedom here. Right, so that's the geometry of omega. Omega is this face. Notice that it is really only 2-dimensional, because as soon as we know the values of any two of the theta, say theta 1 and theta 2, we immediately know the value of the remaining parameters, theta 3. That's an octant. Okay, octant. The fact should always be remembered. This fact should always be remembered when we're dealing with multinomial models. Okay, so here, even though we write theta 1, theta 2, theta 3, we should bear in mind that only 2 arguments are quote-unquote free variables. Okay, suppose we observe a sample of n from this distribution. Suppose we observe a sample of n. By the way, what's the joint distribution? Sorry, what's the joint probability mass function of multinomial models? Let's write it down in our note. Example 6.1.5, recall. So if I have x1, x2, x3, follows multinomial, and theta 1, actually, should I use something else? N is the sample size. Let's use big N, shall we? Okay, and theta 1, theta 2, theta 3. Okay, the theta 1, theta 2, theta 3 are positive or non-negative. Here we use non-negative. Okay, so it includes the boundary. And theta 1 plus theta 2 plus theta 3 is 1. When k equals 2, this corresponds to p and minus p. Exactly. When k equals 2, you only have 2 responses. We don't write theta 1 and theta 2. Instead, we just use one parameter typically. Okay, so that's the constraint. The probability mass function f x1, x2, x3, long subscript x1, x2, x3. Okay, is big N factorial over x1 factorial, x2 factorial, x3 factorial, theta 1 to the x1. This is a direct generalization of the binomial formula. Theta 2 to the x2 and theta 3 to the x3, where x1 plus x2 plus x3 is big N. And they take integer values, non-negative integer values, x1, x2, x3 are greater or equal to 0 and integers, and are integers. So non-negative integers, basically, with this constraint. So not only the parameters have constrained, the variables also constrained. All right. So let's imagine now you have a sample. Now you have a sample. So a sample of size n, assuming independence. What do we mean by that? What do we mean by that? So, sorry, SK is an observation from the multinomial model. So for each k, okay, so let's imagine labeling the, yeah, no, actually not k. K is the maximum, not the maximum, but the number of responses. Okay, so basically what I'm saying is for each of S1 all the way to Sn, it belongs to the set 1 all the way to k. And here we can write down the likelihood function. The likelihood function does not need to include the big, okay, combinatorial coefficient here, because it has nothing to do with theta. Remember, the likelihood function is considered as a function of the parameters only. Okay, so but how should we write the formula? How should we write the formula? Well, what's for example the likelihood for just one data point? Well, S1, as we mentioned, k equals 3. So S1 is either 1, 2, or 3. If S1 is actually, you know what? Multinomial distribution. Yeah, this is correct. You can use the multinomial formula directly. So you have the sample of size n, sample S1 all the way to Sn. In this sample, you can count how many 1, how many 2, and how many 3s. Count the frequency, the raw frequency, okay, not relative. The raw frequency. X1, X2, X3 are outcomes. No, hi Vernon. So X1, X2, X3 are the number of i's. Okay, so X1 is the number of 1. Let's do an example, shall we? So imagine you have n equals 10. For example, n equals 10. Let's use k equals 3. So S1 all the way to S10 looks like this. So this 10 tuple looks like 1. By the way, you can only take 1, 2, or 3, right? By the way, the values can only be 1, 2, or 3, or 1 all the way to k. So it's 1, 2, 3. So it's 1, 1, 3, okay, 2, 2, 2, 3, 1, 3. How many are we? You need one more, 1. Okay. Okay. So if this is your sample, this is already observed, then you can immediately calculate x1. You just count how many ones. How many ones? Raw frequency. x1 equals 4. x2 equals x2 equals 3. And x3 equals 3. So that's it. That's the meaning. So you're going to count the raw frequency of occurrences of I, denoted as xi. Right? So a good way to understand this is to go back to the binomial distribution. Meaning the random oracle. Yeah, I generated these random numbers. Okay, so it's a good way to understand this is to go back to the binomial distribution. So what does the standard binomial distribution do? It counts the number of heads, right? You toss a coin, you count the number of heads, and that's considered as a scalar valued random variable. But if you really think about it, if say k equals 2, the multinomial distribution with k equals 2 is equivalent to the binomial distribution with no loss of information. So the multinomial distribution counts two outcomes, head and tail. Right? But the thing is, if you know the total number of heads, and you know the total number of trials, which you always do, then the total number of tails is determined. So you just need one number there, right? So here, when we say a sample, in the binomial situation, you're really talking about a sample path, head, tail, head, whatnot, blah, blah, blah. Okay, and then you just count the number of head and tails in there. So here we're doing the same. In the sample, this sample really is a sample path, like a trajectory. The outcome of the first experiment, the outcome of the nth experiment, all the way. So you're just going to count the number of eyes. And, of course, by definition, L, theta 1, theta 2, theta 3, given the sample S, is numerically the same as the probability mass function. Okay, is numerically the same as the probability mass function, so you can just borrow the formula here. But of course, this constant at the front does not matter. As we said earlier, you can multiply a likelihood function by any constant, and the result is still a likelihood function. Hi Andre, do you have any opinion on the I have no idea, because I don't know the book. I have no opinion on that book, but I can take a look at it. Okay, so let me just copy that down. I can make a quick comment right now because that will be pretty much meaningless information. Okay, I cannot comment much. Okay. And it appears to be a very thick book. It's 600 pages and whatnot. So yeah, I cannot comment on this. I'm sorry. I have to right now. I have to focus on this problem. So this is proportional to theta 1 to the x1, theta 2 to the x2, and theta 3 to the x3. So this is a function, as I mentioned, defined on the simplex. Omega, the parameter space, is the simplex in the 3 space. So likelihood function is essentially a ranking of points on this 3 space. Based on the lecture series. In the binomial distribution, the random variable whose PMF you define is the number of heads you get. Yes, exactly. You're totally right. You're totally right. In the 4 multinomial distributions, however, you count all the outcomes. Right? In binomial distribution, you can think of it as counting heads. Right? In IID Bernoulli trials, but in multinomial distribution, you also count the tail. But of course, if in the binomial scenario, if you know the number of heads, you already know the number of tails immediately. So for convenience, we simply just write the number of heads, right, in the binomial scenario. Okay, so that's the likelihood function. The likelihood function maps a point on omega, okay, to the real line. So that's what the likelihood function does here. Okay, so let's keep reading. Using the fact that we can treat positive multiple of likelihood as being equivalent, we see that the likelihood based on the observed counts, these are observed counts, is given by this. Okay, so you can think of replacing S1 all the way to Sn to x1, x2, x3. And there's no loss of information here because remember last time we talked about the so-called likelihood principle. So imagine you don't have access to the sequence of trials. So you don't know exactly what S1 all the way to Sns are. You don't know. Okay, S1 all the way to Sn are supposed to be values in, each of them should be values in 1 to k. Suppose you don't have that information. Instead, you only have the counts. And because the two functions are identical, by the likelihood principle, we do not distinguish the two. Okay, the inference about zetas are completely the same. That's the likelihood principle we mentioned last time. Let's go over that real quickly. So likelihood principle says if two models and data combinations yield equivalent likelihood functions, then inference about the unknown parameter must be the same. So likelihood principle is not a God's commandment. Okay, so this is just something that that you may or may not choose to use. You can use likelihood function as a tool in your inference toolkit. Okay, of course, it's a very important one, right? But you don't always or uniquely rely on it. Okay, so likelihood function is something, of course, highly useful, not just in the frequentist paradigm, but also in the Bayesian paradigm as well. Okay, and among other things. The thing is, in practice, you would rarely only rely on the likelihood function alone. However, if you are to do so, the practice will be called likelihood principle. Okay, the principle dictates that everything you want to say about the unknown theta is based on L. Okay, for many statisticians, this is viewed as a very severe prescription. This is a very extreme approach. Okay, nevertheless, it is valuable theoretically. Now, in practice, you would probably also consider things like model complexity. You don't just want the highest possible likelihood. You might also want to penalize more complicated models. So the combination of the combined metric that takes into account both the likelihood value and model complexity is called an information criteria, such as AIC and BIC. But we digress. Right? So according to the likelihood principle, the two functions are completely identical. Therefore, the inferences are the same. The inferences about the theta are the same. This is identical to the likelihood function as function of theta 1, theta 2, theta 3 for the original sample. It is certainly simpler to deal with counts rather than the original sample. This is a very important phenomenon in statistics and is characterized by the concept of sufficiency. So imagine your original data set. Right? This is what is S. S is a member in 1 all the way to k to the n, right? Cartesian product. That's an n tuple. And of course, as sample size grows, the dimension of S grows too. However, it turns out that you can, by appealing to the likelihood principle, you can just consider x1, x2, and x3 alone. Remember, x1, x2, x3, the size of this set of numbers, okay, so the size of this 3 tuple is dictated by k. Here k equals 3. So x1, x2, x3 remains 3 numbers even as the sample size n grows. So that's a very convenient criteria, right? So if we wish to construct such things, we wish to construct such useful summaries of data so that there is no loss of information. And that's exactly the idea of sufficient statistics. Okay, let's go. The equivalence for inference of positive multiples of likelihood function leads to a useful equivalence among possible data values coming from the same model. Remember, data values can have high dimensionality. Right? So the idea is if we can partition the data space or the sample space into equivalent classes, then we can quotient out essentially irrelevant information as far as the parameter is concerned. For example, suppose data values S1 and S2 are such that the likelihood functions differ only by multiple of constant, exactly. So that's a situation where we can consider S1 and S2 are equivalent. From the point of view of likelihood, we're indifferent as to whether obtain the data S1 or the data S2, as they lead to the same likelihood ratio. right? So once again, another analogy can be drawn between mathematical statistics and economics. In economics, there is something called the indifference curve. So in economics, let's consider you only have two goods, okay, pizza and cookies. Right, suppose you have a bundle here, right? The point represents the quantity of pizza and quantities of cookies, slices of pizzas and numbers of cookies. Let's say you ask the consumer a simple question: how many slices of pizza are you willing to give up in order to gain certain cookies, in order to gain a certain amount of cookies? So you start from one point and you keep making such trade-offs so that the consumer is equally quote-unquote satisfied. Then you can trace our so-called indifference curve. Indifference set. Okay, so on each indifference curve, all the bundles of goods are equivalent. And of course, you have different indifferent curves. Typically speaking, quote-unquote higher indifference curves represents higher degrees of happiness. So here in the mathematical statistics, what we're dealing with is sample space. Okay, not parameter space, so we're dealing with sample space here. Okay, so if the two sample values S1 and S2, by the way, S1 and S2 can be vectors. Okay, so S1 and S2 can be can have high dimensionalities. Okay, and if the resulting likelihood are equivalent, then we call them equivalent. You're indifferent to data set S1 and data set S2. Imagine you can partition sample spaces into equivalent classes. Okay, this leads to a definition of a sufficient statistic. Let's go. Definition 6.1.1. A function t, okay, defined on the sample space S, is called a sufficient statistic for the model if whenever t of S1 equals t of S2, so namely two samples, S1 and S2, give the same t value. Then what? Then the likelihood function produced by S1 is a scalar multiple of the likelihood function produced by S2. And the scalar, okay, the multiplicative constant, is a function of S1 and S2 only. It cannot depend on the parameter. Because if it depends on the parameter, then there should be a dot here. Right? This dot stands for the parameter. So that's the definition, motivated by what we've seen earlier. Okay. So the terminology is motivated by the fact we only need to observe the value t for the function big T, as we can pick any value little s that comes from the inverse image or the pre-image of little t under the function big T. So you can think of this as level curves, right? This is basically level curves. In multivariable calculus, we call this level curves or contours. So we are quotienting, we're introducing an equivalence relation on the sample space. So in each equivalence class, the t value, the sufficient statistic t, has the same value. Okay? And all of these choices give the same likelihood ratio. Let's take a look at an example. First, we've already seen the multinomial example, but let's just write that down formally. So t as a function of S1 all the way to Sn equals x1, x2, x3, right? Where x1 is the number, xi equals the number of I in S1 all the way to Sn. I wish I understood the mathematical connections when I studied these topics. So yeah, that's the formal way to conclude this example. And of course, we also, if we also go back to our previous stream, okay, we can look at our own notes, or we can take a look at the textbook. Right? Just look at the textbook. So here, in a normal model, location normal model. So in the location normal model, the variance sigma naught square is constant. I'm going to only say that it's unknown. And after some algebra, blah, 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 we get the likelihood function. You see, the likelihood function depends on the sample only through x bar. Only through x bar. So x bar is a sufficient statistic. And the full phrase should be sufficient for what? Right? Sufficient for the model. Right? Sufficient for the model you're considering. Sufficient for, as far as theta is concerned, x bar is sufficient. Right? And of course, this is not the only sufficient statistic. Right? Any scalar multiple, or any one-to-one function, in fact, any one-to-one function of x bar is also a sufficient statistic. Things like the sum of all the xi's, x1 plus all the way to xn, that is also a completely valid choice for sufficient statistic in this situation. Right? So yeah, so now we have concrete examples. And by the way, what's the equivalence classes in the normal model? What's the equivalent classes in the normal model? Well, in a normal model, x1 all the way to xn lives in Rn. That's the sample space. Rn is a sample space, n-dimensional Euclidean space. So if we define T to be simply x1 plus all the way to xn, that's T. If T equals constant, then the xi's live in the plane. And these planes are all parallel and all perpendicular to the line span of 1, span of the vector 1. Vector 1 stands for the vector whose components are all 1. So these are the equivalence classes over the sample space. They all give the same T value. So that's the equivalence classes imposed by the sufficient statistics here. Okay? If you pick one particular plane and you select two arbitrary points on them, the resulting L function are the same. The resulting L function or differ by a multiplicative constant, meaning they're equivalent. So that's the equivalence classes imposed by the sufficient statistic T, the sum of xi. So this is similar to the notion of indifference in different sets in economics. Right? You do not distinguish two points on the same surface. All right, so that's examples of sufficient statistics. Now let's take a look at more examples. So this is an example of data reduction, which simplifies the analysis somewhat. Of course, we wish to do this as much as possible, okay? And this is a kind of getting ahead of ourselves. But basically, the notion of sufficient statistic is the ancestor of modern dimensionality reduction. Is this always doable? It turns out it is not always doable. The notion of sufficient statistic is in fact highly restrictive. What do we mean by that? Well, a characteristic of the sufficient statistic, okay, a useful sufficient statistic T, is as follows. We want the output of T to have constant dimensionality even when the sample size grows. Right? That would be ideal. Take a look at the multinomial scenario. Even when n grows, the count only has 3 numbers. Doesn't matter how big your n is, the count stays the same. The number of counts stays the same, only 3. And the same goes with the normal location normal model. Right? It doesn't matter how big your n is, t is just one number. And that's what we wanted. We want the value of the sufficient statistic to stay in a space with constant dimensionality. And that turns out to be a huge restriction. Okay, that turns out to be a huge restriction. And as it turns out, only so-called exponential family have this property. Okay, the notion of exponential family encapsulates many of the common distributions. Many of the common distributions, things like binomial, with of course certain restrictions. In binomial, n has to be fixed. That counts as a binomial, counts as an exponential family. A normal distribution is an exponential family. Many common discrete and continuous distributions belong to the exponential family. A Poisson distribution, also a member of the exponential family, etc. Okay, but the principal reason, or at least the original motivation for introducing the exponential family in mathematical statistics has to do with sufficiency. Let me just quickly show a Google page. It's called Pitman, Cooperman, and Darmo theorem. Okay, so we're getting ahead of ourselves, but I just wanted to warn that the notion of sufficiency, although it's nice, it is highly restrictive, and it's because of this theorem. According to PKD's theorem, among families of probability distributions whose domain does not vary with the parameter being estimated, so we want the support of the distribution, the support of the density to remain the same. Okay. Among these families, only in exponential families there exists a sufficient statistics whose dimension remain bounded as the sample size increases. And that's the significance, at least the original motivation for introducing the exponential family. Okay. Exponential family, by the way, has this general form. Here, where is that? Yeah, the exponential family has this general form. Right? If you've taken mathematical statistics or something called the generalized linear model, you might have seen this. Okay. So this encapsulates a lot of common distributions, as I mentioned here, normal, chi-square, Bernoulli, blah, blah, blah. Okay. But the real importance is not to summarize all these distributions to do derivations more quickly, but it has to do with sufficient statistics. Right. Classical estimation sufficiency. If you want to have a sufficient statistics, okay, whose dimension remains bounded, then it only works for exponential family. Okay, then it only works for exponential family. Yeah, there's another restriction. Okay, the support should not depend on the parameter. Okay, that's another restriction. Okay. Okay, so that's this is, by the way, a video under making, because essentially the proof of this theorem is a linear algebra result. Okay? The derivation of the form of exponential family is also a linear algebra result. Okay. All right, so let's get back to the sufficient statistic notion. Right? Even though it is quite nice, it turns out to be highly restrictive. Let's take a look at more examples. Here, example, suppose that S equals 1, 2, 3, 4, omega equals AB. Let's think about what these mean. S is the sample space. Okay, 4 outcomes, 1, 2, 3, 4. Okay, these aren't actual integers, it's just labels. Okay, 1, 2, 3, 4, you might as well just call them alpha, beta, gamma, delta. They're just distinct labels. And omega AB, these are also labels. Okay, is there a reason why we want or don't want? It's just of course we want, right? Imagine that. Imagine the dimension of t grows as n grows. This would not be very convenient, no? This would not be very. Imagine now. Let's say this is a normal scenario. Okay. Imagine the dimension of the values of t grows as n grows. Then it would not be very useful, huh? Like the way you partition the sample size changes. The way you partition the sample space changes as the sample size gets larger. You don't really want that, no? Okay. You want your the idea is to have the sufficient statistic that has fixed or at least bounded dimensionality. And that turns out to be a huge restriction on the form of the distribution. So you can think of this as a quote-unquote characterization theorem of exponential family. PKD theorem, you can think of it as a characterization theorem. So what do we mean by characterization theorem? Characterization theorem has this general format. You want certain characteristic to hold, and that completely fixes the form of the distribution. And for example, one that is done on the channel is rotational invariance and Gaussian. Rotational invariance and Gaussian. If a joint distribution has independent components and is also rotationally invariant, it has to be Gaussian. So that's an example of a characterization theorem. And also there are many other characterizations for Gaussian. Here, this is a characterization for the exponential family. If the probability distribution has constant support, okay, constant support meaning the domain does not vary with the parameter, and it has a sufficient statistics whose dimension remains bounded as the sample size increases, then it has to be exponential family. So that's the characterization theorem for exponential family. Okay, so here let's get back to the main example. Okay, so essentially you only have two competing models. Theta equals A, theta equals B. Theta equals A, that's one distribution. Theta equals B, that's another distribution. Theta equals B in particular is uniform. Theta equals A heavily favors S equals 1. So that's the two competing distribution we're talking about. And here, of course, given the format of S, data point is just one value. Data point little s is just one value. Okay. Does this model has a sufficient statistic? Well, there's not much simplification to be done, right? Because here the data point is just one value. Here the data point is just one value, but let's still try to apply the definition of the sufficient statistic and see what we can get. All right. So notice in this table we have L, okay, L when S equals 2 equals L when S equals 3. So what does that mean? What is L when L equals 2, when S equals 2? Okay, so it might worth making a separate note about this. So here, this is a complete model. 6.1.6. Okay, this is a model. S goes 1, 2, 3, 4. Theta equals AB. 1/2, 1/6, 1/6, and 1/6. 1/4, 1/4, 1/4, and 1/4. So what is L when S equals 2? Remember L, okay, S is, big S is 1, 2, 3, 4. Big omega, the parameter space is AB. Always remember, L is a function that maps from omega to real. Okay, so that's what we're going about. So L dot given 2 is what? L dot given 2 is as follows. You can put it as a table. So the variables are A and B. When the variable equals A, well, since S is 2, right? So you just look at the probability values. When S equals A, sorry, when S equals 2, L of A is 1/6. Okay. When S equals 2, L of B is 1/4. So that's L given 2. Right? L given that S equals 2. But you notice that the last three columns are all the same in the table. The last three columns are all the same, so therefore the likelihood function when S is given to be 2, 3, and 4 are all the same. Remember, identical function means identical domain, identical codomain, and identical values. Okay, so these three likelihood functions are all the same. Okay, so yeah, there you go. That's the value here. So the data values in 2, 3, 4 all give the same likelihood ratio. And as we mentioned, if the data gives same likelihood ratio, if the data gives the same likelihood ratio, they're considered equivalent, huh? So 2, 3, and 4 are considered equivalent. So you can partition the sample space S into two sets, 2, 3, 4, and 1. The set is now divided into two equivalence classes, 1 and 2, 3, 4. Right? You just need a function that can distinguish the two. That will be enough. Okay, so you can just distinguish a function. You can just, if you can distinguish the two classes, it will be enough. So S from 0 to 1, this is not a unique choice, by the way. T1 equals 0 and T2 equals T3 equals T4 to be 1. That will be it. Okay. So of course this is not a unique. This is not a unique choice, right? You can put any two distinct values here. As long as they're good enough for separating the two classes, then you're fine. That's a valid sufficient statistic, right? So this simplifies the model a little bit. It simplifies, in particular, the sample space a little bit. You just now need to consider whether S is 1 or not. You don't care whether it is 2, 3, or 4. So as far as our data point is concerned, we just care whether it is 1 or not 1. Okay, cool. So next we have a important theorem, which is rather easy to prove, called the factorization theorem. Okay, assuming you have a continuous or discrete distribution. Okay, for the continuous case, you use the density function. For the discrete case, you use the probability mass function or simply probability function. Same thing. So if the density can be written in such form, the density f theta of S can be written as h of S times g theta of T of S. So what does this mean? On the left-hand side, of course, is the original density. On the right-hand side is a factorization, the namesake of the theorem. The factors are hs. This is a function that depends on the sample only. Okay, no theta involved. And the second factor, depends on theta by the notation g theta, whose argument is T of S. So g is a single variable function, or at least it's not a single variable in the sense that this g theta, the function g theta, has as many arguments as in the domain of T, if that makes sense. And they really says the book introduces formal probability theory, but also gives great introduction. Okay, great. Yeah, if you like a book, then if you want, of course. Actually, that's shot. So if you guys have your insights and particular recommendation on what the book is good for, Go ahead, and I encourage you, don't have to, but I encourage you to share it in the book recommendation channel. Okay, so this way people can see if the book suits their own need, right? But it sounds like anything that balances abstract and concrete thinking gets an endorsement from me. Okay, so I will likely enjoy that book too. Okay, so that's the factorization theorem. Well, before looking at the proof, why don't we look at an example? Now, why don't we look at an example? For example, the normal model. The normal model revisited. Right. Here we calculate the likelihood function. And notice that x bar is sufficient. But can we just use the density? Okay. So let me first write down the statement of the factorization theorem, and then let's redo the normal example. Factorization theorem. I think this is called Fisher-Niemann theorem. Theorem 6.1.1. I think this is called Fisher-Niemann factorization theorem. And a full general statement based on measures theory was given by Paul Holmes and L.J. Savage, I believe. Okay, so this is the Fisher-Niemann factorization theorem, which later generalized to Paul Holmes and Savage. Yes, that Holmes and Savage theorem. So Holmes and Savage give the full measure theoretic statement. Okay, here we're only dealing with the special cases here, which is sufficient for us. No pun intended. So here it says f theta of s equals hs times g theta of t of s. So g is a function of t. No, g is a function of t. Is a function of t, and then t is sufficient. For theta, so that's the theorem here. Okay. But let's look at an example before we look at the proof. Example: normal family, location normal family. Here. Example 6.1.4. Okay, f theta of x equals 1 over 2 pi, just a single density, square root of 2 pi sigma naught e to the negative x minus theta squared over 2 sigma naught squared. Can we write it as a function that has this form? This is a location normal family, or location normal model. Theta is real. That's the parameter space. Can we apply the factorization theorem here? Well, to apply it, we first need to do a little bit of a manipulation, as it seems, because we need a product form. We need a product form. Here, s and x and theta are intertwined. Actually, you know what? This is not quite right. This is not quite right. This is not just a. Okay, so still, this is not the joint distribution yet. Okay, this is not joint distribution. The f theta of s is f theta of x1 all the way to xn. Okay. So that's based on the ID assumption, or the product over I from 1 to n is 1 over square root of 2 pi sigma naught e to the negative x minus theta squared over xi minus zeta over 2 sigma naught squared. Okay, and let's do the manipulation here. So you get 2 pi raised to the minus n over 2 sigma naught raised to the minus n. And you get the exponential of negative 1 over 2 sigma naught squared. And the sum of xi minus zeta squared. I from 1 to n. Summing over from I from 1 to n. Okay? And we wish to write it as a product form. How to do that? How can we use the factorization theorem? We know t should look like the sum of xi. That's what we know. Remember, zeta naught is treated as constant. Can we factorize this? Use the theorem? Can we do that? My problem is if you expand this, you get an xi squared too. Oh, that's okay. That's okay. Because xi squared has nothing to do with zeta. So let's expand. Okay, let's do that. 2 pi. I just want to illustrate the factorization theorem before proving it formally. The exponential of minus 1 over 2 sigma naught squared sum of xi squared. I from 1 to n. Okay, and then plus 2 zeta sum of xi, I from 1 to n. Once again, divided by 2 sigma naught squared. And lastly, you have negative 1 over 2 sigma naught squared sum of zeta squared. Sum of zeta squared, which is just n times zeta squared. Okay, so that's just the expansion. Okay, so now let's group things. Remember, sigma naught is treated as constant. Let's look at things that has nothing to do with zeta. So HS has nothing to do with zeta here. Let's emphasize that. In HS, no zeta. No zeta appears. And in the second function, right, it must depend on zeta and the sufficient statistic. So how we can break things up? Well, you got 2 pi raised to the minus n over 2 sigma naught to the minus n exponential of minus 1 over 2 sigma naught squared summation of xi squared. This is nothing but HS. See, this has nothing to do with zeta. And the rest, the exponential, let's simplify that, of zeta over 2 sigma, not 2 sigma, but just simply sigma naught squared times the sum of xi minus n zeta squared over 2 sigma naught squared. This is our h, not h, g zeta of t of s. Okay, it depends on zeta and also depends on the sufficient statistic, the sum of xi, where t is the sum. So you can identify the portion that only depend on the sample and call that the sufficient statistics. Quick question, but what are you trying to write in OneNote? Like a just PC. It's just PC. It comes with standard Windows applications, Office. Now this is OneNote in my PC. I'm writing it with my mouse here. So here, this is an illustration of the factorization theorem. I mean, this is not terribly superior, say, than just evaluating the likelihood function in the original example. It's not terribly more convenient than that, but it is certainly valid. Right? It's certainly valid. So you can identify the form of sufficient statistics by attempting to factorize the joint density. Okay. So let's take a look at the proof. All right. So first we have assume the hypothesis is true. Okay. Assume f theta has this factorization form. So by the hypothesis, it is clear that when t, okay, we assume there is a statistics t. Okay, we assume there is a statistics t. A statistic, by the way, is a function of the sample only. The statistic is a function of sample only. It depends on the sample value, and potentially depend on the sample size too, but no dependency on the parameter itself. Okay, so we assume that T1 and T2 are the same. Why is that? Because in the definition of sufficient statistic, we assume whenever T1 and T2, T of S1 and T of S2 are the same, the likelihood, the corresponding likelihood are equivalent. Right? So we assume the assumption in the definition. I just finished writing a statistics-based proof yesterday, and symbolic math was just too much for me. You mean, well, you probably need to typeset it, huh? Using LaTeX or just use Word or Office, the built-in editor in Office. Right. I very much just use the built-in in Office. Okay. I mean, I do use LaTeX for more formal setting, but for YouTube, I just use the Office tools, like MS Word and PowerPoint. Seems enough to me. Well, and thank goodness I don't do much algebra. Right? If I do algebra, then the commute diagrams would be difficult to handle. And then I have to use LaTeX. But then again, I'll probably never going to write a paper in algebra. But we'll see. Okay. Okay. So here we have this assumption: T of S1 equals T of S2. So by the assumption in the factorization, L factorizes. Right? Remember, L numerically is just the probability density or probability mass function. Okay, so this factorizes. Okay, so now because of we try to use the assumption. Okay, we try to use the assumption that T. Actually, you know what? This looks rather awkward. Why don't we take the ratio? Okay, let's look at the proof and write our own proof. Why don't we take the ratio of L of S1 and L of S2? Okay. Proof of theorem 6.1.1. Okay, assume the assumption part in the factorization theorem. Assume f theta of S equals H of S G theta of TS. Okay, assume that. Suppose S1, S2 satisfy T of S1 equals T of S2. And let's calculate the ratio of L theta given S1 over L theta given S2. Let's calculate that. So first, by the definition of likelihood, this is f theta 1 of S1 over f theta of S2. Okay, and then use the factorization assumption, you get h of s g theta t of S1 Okay, right now we're not assuming t is sufficient. Okay, we're not assuming t is sufficient. We assume this, we need to prove t is sufficient. Because that's the result, then part. Then t is sufficient. Need to show t is sufficient. Okay, so that's the logical structure here. And for that, let's assume t of S1 equals t of S2, and we need to show that the likelihood are equivalent. So hopefully that's clear. Okay, so use the factorized form of the likelihood. Of course, h cancels out. And what remains is simply g theta of ts1, t of s1, over g theta of t of s2. Hang on, sorry, this is h1. H does not cancel, my bad. These do not cancel. So actually g cancels, in fact. G cancels, in fact. So you just get h of s1 over h of s2, which is a function of h1 and h2 only. No theta remains. And that's exactly what we wanted. What are f and g models? No. F is the distribution. F is basically the model. F is basically the model. H and G are just non-negative functions. Okay, some function. They don't have to be densities or anything. Remember, in our example, in our normal example, h of s is this monstrosity. It has nothing to do with, it's not a density per se, right? G is not a density per se either. It's just a function. F is a model. Yes. All right. So here we can just call that C of S1 and S2, which by the definition of sufficiency, do we have that here? Oh, actually, I didn't write that down. My bad. I should have written that down. I should have written that down. So let me fix that real quick. So we need the definition of sufficiency here. Definition of sufficiency says if the t value are the same, then the likelihood are equivalent. Okay, t from S to, well, Rk is sufficient for the model p theta. Okay, p theta is a family of distribution. Is sufficient if whenever t of S1 equals t of S2, the resulting likelihood are the same. Or not the same, but are equivalent. So that's the definition of sufficiency. So by the definition of sufficiency, we indeed have t is sufficient. So by the definition of sufficiency here, t is sufficient, QED. Okay, so this is the definition of sufficiency in the textbook. I just want to briefly remark that you might see a different definition, but it should be equivalent. I think it should be equivalent, but yeah, let me just put that down. Okay, why don't we just call that a corollary or something, or not a corollary, but rather a proposition. Proposition. So equivalent characterization. Of sufficiency. Okay, so a statistic T is sufficient for the model T is sufficient for the model P theta if and only if the conditional distribution of the sample given T does not depend on theta. Okay, so this is actually the distribution, sorry, this is the definition of sufficiency in Castellan-Berger. Okay, this is also the definition of sufficiency in the book by Castellan-Berger. We just finished writing that sentence. If the conditional distribution of S given T does not depend on theta. So this is the same business of the equivalence class we're talking about. So this is the same business as we imagine if you have, say, what's the picture here? If you already know that the point is on one of the equivalent classes, then the exact knowledge regarding the point, regarding the data point, cannot tell you anything about theta anymore. So that's the definition given by Castellan-Berger on sufficiency. So sufficiency has a different characterization. T is sufficient for the model if and only if the conditional distribution of S given T does not depend on theta. Okay, so why don't we look at an example? Before proving it, I want to look at an example. Does this show up in the text? Let me just quickly check that, okay? Because I quite like that definition as well. It's not here. It's not here. So let's try to first see an example of this. See an example of this proposition and do a proof. Okay, prove this is equivalent to the definition of sufficiency given by Evans and Rosenthal. Okay, let's first look at an example. And just to make things simple and easier to visualize, let's just say x1, x2, IID, normal theta, sigma naught squared. So this is your S here. S equals S1, x2. x1, x2. That's the... And of course, we know that from earlier, we know the sufficient statistics is the sum of x1, x2. By earlier, T equals x1 plus x2 is sufficient. Okay, so let's look at the geometry here. What is going on?
S, the sample space, is simply the Euclidean plane. Okay, and let's imagine what the distribution is like. What the distribution is like when you vary theta. First of all, what is this distribution? I'm talking about the joint distribution here. Okay, the joint distribution is bivariate normal. So S as a vector is bivariate normal. BVN, okay, whose mean vector is theta theta. Okay, the mean are the same. And what's the covariance matrix? Well, the covariance matrix due to ID assumption is simple. It's simply sigma naught squared 0, 0, sigma naught squared, because the off-diagonal terms are covariances, which are 0. So this can be equivalently written as matrix vector notation, BVN theta times the vector 1. Okay, and then sigma naught times the identity matrix I. Okay, so the covariance matrix is a constant. And the mean vector lives in the space span of 1. The mean vector lives in the space span of 1. So let's draw that. This is the span of 1. This is the span of 1. So the mean is on this line. It has to be on this line. Here we're drawing, once again, the sample space. The mean vector can only be a straight line, be on the straight line of that sample space. Okay, so that's the intuition. Let's draw a typical distribution. How do we visualize the distribution on R2? Well, let's use equidensity contour. Okay, what's the equidensity contour look like? Well, these are circles. What's the density of S? Density of S, F theta of S, is really easy to draw, which is 1 over 2 pi square root, use ID assumption, e to the x squared, e to the minus x1 minus theta squared over 2 sigma naught squared times 1 over square root of 2 pi e to the minus x2 minus theta squared over 2 sigma naught squared. Okay, and then you combine them, you get 1 over 2 pi e to the negative. Actually, you know what? Let's use exponential. This way, the exponents is easy to write. 1 over just 2 fraction x1 minus theta squared plus x2 minus theta squared over what? Over 2 sigma naught squared. Okay, so the equidensity contours are circles. Which to nobody's surprise are circles. You just need to keep x1 minus theta squared plus x2 minus theta squared constant. The constant. The constant depends on the value of the density. The higher the value of the density, the smaller the circle is, because you want the density to be concentrated in a small point, right? So that's if the density has low value, then the radius is large. So let's just draw a bunch of concentric circles to visualize the bivariate normal distribution. Okay. Because I know you guys like geometry of statistics. So that's the model interpreted geometrically in the sample space. So, okay, so this roughly looks concentric, okay, to me. So that's basically a model. This corresponds to one model. This corresponds to one model. The center is on the line. And as you vary theta, these concentric circles moves along the line, like this.
Okay, this is one model. Okay, and what is x1 plus x2? What is x1? What does x1 plus x2 does? Well, constant x1 plus x2 are lines with slope -1. Constant t equals x1 plus x2. So you are collapsing information. You're collapsing the points along the red lines. So these are equivalent data points. On each red line, all the points are considered equivalent because they give the same value of the sufficient statistics. So it's like by calculating a sufficient statistic, you're projecting the data point onto certain quote-unquote directions of the sample space that matters to theta. Because as theta varies, the distribution only slide along this line here. Only slide along y equals x, right? x1 equals x2. And by calculating a sufficient statistic, you're collapsing the data points onto that line. Right? And all the points that are orthogonal, right? Or the sets that are orthogonal to the span of 1 are the equivalence class. So if that makes sense. Okay, so what does that has to do with a proposition? Well, let's consider what happens when you condition on t. Can we condition on t and calculate the distribution of t1 plus t1 and t2? It turns out we can. So let's consider something else. Let's consider t1 minus t2. I'm trying to calculate the conditional distribution of x1, x2 given t. Okay, so how do we get to that? Well, let's consider the orthogonal direction because this is rather natural. This is rather natural. So we have one direction, that's the direction of these red lines, slope with 1. What about the lines that are orthogonal to those? So let's consider d equals x1 minus x2, the difference. Consider d equals minus x1 minus x2. We can easily show that d and t are independent. D and t are independent because the covariance between them is 0. Okay, so you know what? I'll just leave it here. Okay, I'll have to take a phone call and I'll be back in a few minutes. But for those of you with access to some sort of note-taking device, yeah, go ahead and calculate it and show this is equal to 0. This should equal 0. Okay, I'll be back in a few minutes. Okay, I'm back. So here, hang on. I think I need to charge my phone. Just 1 minute. All right, guys. So let's calculate the covariance of T and D. This should be rather easy. Just use bilinearity. Covariance of x1, x1 minus the covariance of x1, x2 plus the covariance of x2, x1 and minus the covariance of x2, x2. So the two terms in the middle cancels. The covariance of x1 and x1, sorry, not x2. This is just the variance of x1. Variance of x1 is, of course, sigma squared, sigma naught squared. And then minus sigma naught squared, which gives you 0. And since T and D are jointly Gaussian, right? Because T is a linear transformation of x1, x2, and so is D. A linear transformation of a Gaussian is always Gaussian. So since, let's write that down, since TD is a linear transformation of x1, x2, TD is jointly Gaussian, or simply Gaussian. And for Gaussian random variables, if the covariance is 0, then immediately you have independence. TD independent, or T independent of D. Let's write that. And T and D are independent. So this is a nice property because the distribution of D can be easily calculated. Since D is Gaussian, you just need to know its mean and variance. The expected value of D is expected value of x1 minus x2 is 0. The variance, this is characterized as MVN. Actually, yes. Actually, yeah. Christian is absolutely correct. He is talking about the famous theorem due to Bernstein and Katz. Okay, this is a cool theorem due to Bernstein and Katz. If you have x1 and x2 independent, and x1 plus x2 and x1 minus x2 independent, x1, x2 must be zero mean Gaussians. Okay, so that's a cool theorem about it characterizes bivariate. It characterizes bivariate, right? So it's pretty much what Christian is saying. Once again, so many cool characterizations about Gaussian, and the proof usually amounts to solving functional equations or differential equations for the density or the characteristic functions. Okay. Anyway, so here we're not going to get into that deep, but basically the variance of D is also easily obtainable. The variance of D is simply the variance of x1 plus the variance of x2, which is 2 times sigma naught squared. Okay, so the variance of D and the expectation of D are both known. You have D follows the normal distribution with 0 mean and 2 sigma naught squared. So why is that helpful? Well, T and D are independent, so immediately you get the conditional distribution of D given T is the same. Since independence, T will not affect the distribution of D. So there's that. Okay. Okay. And x1 and x2, because they have fixed sum, if you know the difference, then x1 and x2 are known. This is a distribution of d given t. And if d is known, then x1 and x2 are fixed. Okay, so let's write it this way. x1 minus x2 given t is normal 0 to sigma naught squared. So the geometry is as follows. Given t, x1 and x2 is a point on one of the red lines. So given, say, big T equals little t, then x1, x2 can be written as follows. Okay, you can write x1, x2 as, say, the sum minus z. Okay, let's call x1 half t. Why don't we call that half t plus z, and x2 to be half t minus z. Half t minus z. And this is the point half t, half t. This is half t, half t. So you just need to know the distance, so to say, from the intersection with the span of 1. Okay, so what's the distribution of z then? Let's write that as follows. Let's write, given, as we said, given x1 plus x2 equals little t, let's write x1 equals half t plus z, and x2 equals half t minus z. Okay, so this way, what's d? D is x1 minus x2 is just 2z. So what's the distribution of z? Well, d is that, and so 2z given t equals little t follows normal distribution with 0 mean, 2 sigma squared variance. Okay, if you divide by 2 on both sides, you get the conditional distribution of z given t equals little t is normal distribution with 0 mean and half. Okay, because if you divide by 2 on the random variable, the variance divide by 4. So it's half sigma naught squared. So half the sigma naught squared. So you can write it this way. Therefore, conclusion. x1, x2 and x2 given t does not have a density because this is degenerate. Okay? The joint distribution of x1 and x2 does not have a density because it is now confined onto a space with 0 measure. Okay, this is a line. Okay, so given t as little t, this has the same distribution. It has the same distribution as half t plus z, half t minus z, where z follows, as you can see here, the distribution of z has nothing to do with t, so we can drop t equals big T as well. So z follows the normal distribution, 0 mean and half sigma naught squared. So this tells you exactly how do you generate a point on the sample, on the line big T equals little t. This tells you exactly how to generate a point. If you know big T, then you can describe the conditional distribution of x1 plus x2, x1 and x2, the conditional distribution. How do you do that? Well, you look at the center, which is half t, and then you're just going to generate a random number z. which has nothing to do with t. Which has nothing to do with t, and then you subtract and minus that value in each component. The moral of the story is this on the right hand side. This has nothing to do with theta. This is independent of theta. This is independent of theta, which is exactly what we're trying to show. The conditional distribution of the sample given t does not depend on theta. Okay, so why don't we look at another example? This is one example. This is perhaps a little bit weird because we're dealing with degenerate distribution. Nevertheless, it is still a valid distribution. The conditional distribution of x1, x2 given big T equals little t is degenerate. It lies on the line. But still, this is a valid distribution. In fact, I posted a quiz not too long ago asking whether every multivariable normal distribution has a density. Whether every multivariate normal distribution has a density. The answer is no, because for degenerate normal distributions, degenerate MVN, degenerate multivariate normal distribution, a density does not exist. Here you have a perfect example of jointly distributed normal random variable that has no density. Given big T equals little t, x1 and x2 is jointly Gaussian. However, it does not have a density. Okay, so it's a singular Gaussian or degenerate Gaussian. Okay, let's look at another example before coming back to the proof. Another example. Let's consider S be x1 all the way to xn, where xi's are IID Bernoulli random variables. Bernoulli with parameter theta. Okay, Bernoulli with random variable theta. So our goal is to find the sufficient statistics Part A. Find the sufficient statistic. I believe this is an example in Casella and Berger. Okay, find sufficient statistic using the factorization theorem. Okay, and part B, show that find a sufficient statistic. Let's call it T. T of S. Using the factorization theorem, that's part 1. Part 2 is to show that S given Ts does not depend on theta, which is the proposition. Okay, so this tells us given the sufficient statistic, given the value of the sufficient statistic, knowing the detail of the sample, do you know good? Does you know good as far as theta is concerned? It tells you nothing. Right? Remember the visual example here. In the bivariate normal case, if you already know t, then knowing this exact position of x1 and x2 does you no good, because the distribution of x1 and x2 does not even depend on theta. So knowing the exact position tells you no further information. All right, so let's do that. So the first one should be rather standard. Let's first write down the likelihood. L of theta given S. What does that look like? Well, that's simply the product of the probability mass function, f theta of xi. As far as Bernoulli is concerned, right, Bernoulli is equivalent to binomial 1. Binomial 1 theta. So use the binomial formula. 1 choose I. 1 choose xi. Theta times xi. Theta times, because xi is in 1 or 0, right? So the binomial coefficient is always 1. Because 1 choose 1 is 1, 1 choose 0 is 1 too. So it does not matter, always 1. Okay, so simplifying, you get theta to the sum of xi. And times 1 minus theta and minus the sum of xi. Okay, So our goal is to use the factorization theorem. Can we write this? Can we write this in this form? A function that only depends on the sample, right? A function that only here, yeah, here. The function that only depends on the sample. This is the form we're looking for. Times g theta of t of s. But it looks like we already have that, right? Because this only depends on theta and sum of xi. That's it. So you can simply take h of s to be constant 1, g theta of t to be theta to the power of t minus, that's right, yeah, g theta to the power of t times 1 minus theta m minus t. See, it only depends on, well, n is treated as constant. It only depends on theta and t. And we have the factorization theorem where t equals the sum of xi. So this is satisfied by the factorization theorem. T is sufficient. T is sufficient. T here, this is a sufficient statistic for this model here. So what does that mean? Remember, x1 all the way to xn are either 1 or 0, right? So the sum of xi is just the number of ones. You just count the number of ones. Note t is the number of ones in the sample. So you don't need the exact sequence, you just need the number of ones. Which seems rather intuitive, right? Right. To calculate, to make information, to infer p. P is, remember, theta. So infer theta. Theta is the probability of equals 1. So you just count the number of ones. That's enough. You don't need a whole sample. Okay, so that's part A. Part B, let's verify this conditional distribution. Yeah, so here it got stuck. The Wi-Fi got disconnected. All right. So I was talking about the part B, right? So we wish to show that the joint distribution of the sample given the value of t, which is the sum, has nothing to do with theta anymore. Okay, so that's the idea of sufficiency. How do we do that? Well, first you have the distribution of t in itself, right? So since xi is RID, Bernoulli theta, the distribution of t is binomial n theta. Just count the number of successes, basically. Okay. Can we calculate the distribution, the joint distribution of xi? Let's try to do that. So I wish to calculate the probability of x1 equals little x1 all the way to xn equals little xn, given that t equals little t. I wish to calculate that. Okay, that's the joint distribution. So let's use the definition first. You have that's the conditional distribution. So we want the joint distribution over the marginal distribution of t. Over the marginal distribution of t. So here, remember, well, because t is the sum of xn, t is the sum of xn, so you can simply write that as x1 equals little x1 all the way to xm minus 1 equals little m minus 1, and the last one, big Xn, is simply t minus the sum of xi, I from 1 to m minus 1. So you lost the degrees of freedom. You lost 1 degree of freedom upstairs. All right, so downstairs we can calculate everything because x1 all the way to xn are independent. So that's just, well, the theta to the x1, 1 minus theta to x1 all the way times theta to xm minus 1, 1 minus theta xm minus 1. Oh, sorry, 1 minus. Did I miss that? No, I didn't miss that. Here, 1 minus. And lastly, theta to the xn, 1 minus theta, okay, 1 minus t plus the sum of xi, I from 1 to m minus 1. So that's upstairs, the joint distribution. And downstairs, as we said, that's binomial. Binomial, you just get n choose t, theta to the t, 1 minus theta to the t, to the m minus t. Right, so let's connect the terms. Collect the terms. Theta has a power of the sum of xi, I from 1 to n. Theta 1, okay, all the way to theta n minus 1 and theta n. So that's the power of thetas. And 1 minus theta has an exponent of what? 1 minus theta has an exponent of well, 1, you got n1, so that's n. Okay, minus what? Minus so it looks like the sum of xi, I from 1 to n minus 1 cancels out. So here this is 1 minus x1 all the way to 1 minus xn minus 1. Here you add all those back so they cancel out, just minus t. And divided by n choose t, theta to the t, 1 minus theta n to the n minus t. So because sum of xi is just t, everything cancels out, you just get 1 over n choose t, independent of theta. Independent of theta. So we're done here. So what does this say? So what does this say? How do we interpret this result? Well, you can think of this way. What happens when you condition on t? When you condition on t, the number of possible samples is now n choose t. Interpretation. interpretation, given big T equals little t. Remember, this means the number of head or number of ones is t. So to specify a sample, you just need to choose t positions that to be 1, so that they are 1. And the rest are just 0. Okay, so given big T equals little t, there are n choose t possible samples. S. S equals x1 all the way to xn. And that's how it's done. So a sample has n positions. S. Okay? And you're just going to choose t of them to be 1, and the rest are just 0. So of course that's n choose t. And leave the rest to be 0. And this interpretation says all those samples are equally likely. The result above shows that all those samples are equally likely. So it tells you nothing about theta anymore. It's just a uniform distribution over possible samples. Are equally probable. Isn't that beautiful? I hate to always add this sort of rhetorical question because this should already be internalized by the individual. Right? So when you condition on the sufficient statistics, the sample value does not matter anymore. So that's the idea. So we're going to prove the proposition. Let's try to prove this proposition. T is sufficient if and only if you have a conditional distribution of S given T independent about theta. Proof of the proposition. I think we're in a good position to prove that proposition. Okay. So which direction should we go about first? Why don't we just assume discrete distribution? Just to get the idea across. That's enough. Can we use the factorization theorem? We use the factorization theorem. Well, the theorem gives a sufficient statistic. Gives a sufficient condition. The theorem gives a sufficient condition to arrive at a sufficient statistic. So why don't we verify this condition in the opposite direction? We'll try to use a factorization theorem here. Okay, so let's do that. So we're going to assume that the conditional distribution of S given T does not depend on theta. And try to prove that the condition for the factorization theorem is satisfied. Then you get T is sufficient. Okay, assume the joint distribution, joint PMF of S given T of S does not depend on theta. Namely, it is a function of S only, independent of theta. i.e. it is a function of S only. So, say, let's write ft of S. Ft of S. This is the condition notation for the conditional distribution. Ft of S is, say, this is h of S. Let's just call that h of S. What do we need? Well, we need the distribution of S. To use the factorization theorem, we need to show f theta of S factorizes. Right, this is the distribution of S. The distribution of S can be, how do we connect to the conditional distribution? Well, you can do this. You can calculate f theta of Ts, S and T, f of little t. Okay, the joint distribution of S and T, and then you sum over T. Right, you can do that. This is the relation between joint and marginal distribution. So now, let's write it this way. We know the joint distribution can be written in this form, namely the conditional distribution times hang on, this is not a good notation. Let me change that. Conditional distribution usually is written this way. Oh, it's a function of S and T only. No, not in. It can depend on T. It can depend on T. So, okay, let's change that. Okay, we can remove that. Okay, can remove that. Okay, so this is the assumption, and the joint distribution is the marginal distribution of T times the conditional. S given big T, little s given little t. Now here we're using the assumption independent of theta. And then times ft of little t. Ft of little t may depend on theta. The marginal distribution of t can totally depend on theta. So just write it this way, okay? So to indicate the marginal distribution of t can depend on theta, and we're summing over little t. So what do you get here? This factorizes? Hold on a second. Does this we want to sum over I, huh? Marginal distribution of t. So we're summing over t. I'm stuck. If it satisfies, I want to show this satisfies the condition for the factorization theorem.
Okay, where do I start? Okay, I assume that the joint PMF of S given T is independent of theta. I want to show the distribution of S can factorize. So how do we say, if we have this part, if we, in the concrete example, if we have that, how we get back to the joint distribution of the sample? Well, you multiply that by the density of oh, actually, you don't need to do the summation. You do not need to do the summation because given S, T is determined. There's no need to do the summation anymore. Because there's no possible values of T given S, remember. Here, of course, this is in general correct, but in here, essentially, you just only have one term in the sum. That's why. Okay, let me just put that down, okay? So the summation only has one term because given S, T is fixed. When S is fixed, T is fixed. Okay, so there's that. It's just sum is just one term. T of S, that's it. And then you use the following. The sum is just one term. Because T is a function of S, remember. Okay, the chat has been very quiet, so are people completely lost now? Okay, remember what we're trying to prove. We're trying to prove that if the joint PMF of the sample given the sufficient statistic, given T is, we don't know T is sufficient yet, okay? We don't know T is sufficient yet. We need to show T is sufficient. We need to show T is sufficient. Need to show T is sufficient, but basically here we're already done. Here we're already done because we can just call the first function h of s here. This is given t of little t equals t of s. We can call this h of s, and it's independent of theta. And here, the second term is a function of s. Is a function of s through t only. So this is our g theta of t of s. So therefore, by factorization theorem, t is sufficient. Okay, so that's done. Can I prove the other direction? The other direction basically says, right, so the other direction is that T is sufficient. Assume T is sufficient. We need to show the joint PMF does not depend on theta. Suppose T is sufficient, or assume T is sufficient. Okay, so this is where something I guess we need to be a little bit careful, because in the factorization theorem, here, in the factorization theorem, by assuming
t is sufficient here, okay, this is the theorem. By assuming t is sufficient, we cannot get the factorized form. At least we don't know. We don't know if there's a counterexample, but basically the original factorization theorem as stated here, I don't know if t is sufficient, you can get the factorization immediately. So here, let's just use the definition of sufficiency only, right, according to the original definition here. Okay. So even though we only did one page, even though we just did only one page today, but I think I added a few more examples to enrich the content. Okay. Hang on. Chat has been real quiet. I don't even know I'm still online. Let me just check the stream on my phone. Okay. Only 2 people remain. Oh God. All right, that's fine. We'll continue to do this. No worries. People might not have time. Okay, that's totally okay. So let's keep going. No. Oh, thank you, Kraken. Thank you very much. So yeah, I was going to say, assuming t sufficient. I haven't really looked into sufficiency before, so this has been really enlightening. No worries. So yeah, assuming t is sufficient, we wish to show, need to show the condition, the distribution, conditional distribution of, and don't worry, sufficiency will have its own standalone video. Okay. Sufficiency will have its own standalone video. Conditional distribution of S given Ts, okay, is independent of theta. So this is what we are going about. Okay. So here, let's consider, first let's try to express the conditional distribution. Let's try to express the conditional f of S given t, little s, t of s. Use the definition. You got the joint distribution, which joint distribution in general depend on theta. S of t of s, s and t of s, divided by, in general, well, the distribution of t depend on theta as well. So let's write f subscript big T, semicolon theta, t of little s. So that's the conditional distribution. Well, on top, we know that, well, this is numerically equal to just the joint distribution of S, because Ts is completely determined by S. Okay. And let's use the definition of likelihood, because the original definition of sufficiency was given in terms of likelihood. Let's use the likelihood formula. The likelihood L of theta given S over the T theta given T of S, okay? So somehow we need to show that S cancels out, sorry, theta cancels out. Somehow we need to show this is independent of theta. How do we do that? Remember, assuming T is sufficient, we want to show this is independent of theta. So we want to show the conditional distribution does not depend on theta. How do we factorize that out?
Okay, so you have the joint on top, that's the joint distribution of the sample. At the bottom, you have the distribution of the diffusion statistic. Can you factorize the likelihood? Yeah, that's what I'm trying to think, right? So I want to somehow cancel this at the bottom. So how do because we never even use the definition of sufficiency, right? At this point, we haven't even used the definition of sufficiency. Hmm. Can we maybe consider a different S? Consider a different S. So you have S over, this is true for all S, right? So let's consider a different S, S prime. Let's call it S prime. Given T of S prime. So this is L of theta S prime over F T. Theta is the same, T of S prime. Oh, by the way, assume T is sufficient, meaning we need to assume two sample have the same, right? We need to have the two T value, have the same T value. Here is whenever T of S1 equals T of S2, you have this. Okay, so let's go ahead and assume that. Let me just erase this. We need that assumption. Suppose S1 and S2. Suppose T of S1 equals T of S2. Then, of course, the two T values are the same. The bottom is the same. Okay. Then F of T theta, T of S1 equals F of T theta, sorry, T theta, T of S2. These two are the same. And yeah, Kraken mentioned, can you factorize the likelihood function? Yeah, you can do so if you assume this. And L what? L is what? L of theta S1 is, by definition, C of S1, S2, namely the two likelihoods are equivalent. So there's that. Let's consider the ratio between two conditional distribution. Consider Fs given T S1 given T of S1. Fs given St S2. Okay, let's consider the ratio. Then denominator cancels, you're just left with the ratio on top. So L of theta S1 over L of theta given S2. And that's just C of S1, S2. Just C of S1 and S2. And I want to show this has nothing to do with theta. I mean, this is independent of theta, right? This is good news. This is independent of theta, but how can we show that this is this implies that the whole conditional distribution does not depend on theta. Well, I think you're already done because you can rewrite this as follows: f of, hang on, that's not okay. I mean, if let's say if you have the conditional distribution does not depend on theta, like the conditional distribution of s given t does not depend on theta, then this must be true. Then then the ratio cannot be dependent on theta. But is the converse true though? Is the converse true? So assume t is sufficient. Assuming t is sufficient, here we're using the definition. Suppose t of s1 equals t of s2. You have this relation. So this way, given the same t, this is the ratio between conditional distribution at S1 versus at S2. This is independent of theta, which is nice. But can we get to the point, can we say that because when we write this, even though theta does not appear, in principle, this can still depend on theta. See, this is the right-hand side. In principle, theta can still appear. You can't just say, oh, theta does not appear here, therefore it's independent, right? So we wish to come from this to say this actually does not depend on theta. So this is a constant function of theta. How can I do that? I think I'm a little bit stuck here. So if we assume t is sufficient, can we get to, actually, you know what? Assume t is sufficient, can we at least get the factorization form? Huh? Okay, assume t is sufficient. Actually, you know what? Here in the factorization theorem, we assumed the form, then showed t is sufficient. Do we have the opposite direction here? Even though this is a one-directional statement. This is a one-directional statement. Is the converse true? Assuming the distribution is either just restrict that to discrete, okay? Because I don't want to deal with general situations. So assume the distribution is discrete, and isn't it true by definition of sufficiency? Kraken. I assumed the opposite direction. I assume t is sufficient. I want to show the conditional distribution is independent of theta. The definition of sufficiency in this book is given as follows. It's defined in terms of likelihood. I want to show this is equivalent to the other definition in Casella and Berger, actually.
Here, this is the definition of sufficiency. I'm using this definition, and I'll try to show this implies the Casella-Berger definition. Okay, so let me just think of the converse of theorem 6.1.1. Is the converse true? Assume T is sufficient. Do we have the factorization form? Because here, this is the opposite direction, right? Let's think about that. So assume T is sufficient. Let's do it on the side. T is sufficient. So that means assuming T of S1 equals T of S2, using our definition, you have L of theta given S1 equals C of S1, S2, L of theta given S2. So that's what we have here. Can we prove that L factorizes? Can we prove that L factorizes? So basically, you can rewrite L as F, right? L as F. You can rewrite L as F. F theta of S1 equals C of S1, S2 times F theta of S2. So yeah, this is the definition of sufficiency. Can we get the factorization form though? Hang on a second. Actually, you know what? The problem is, how do we introduce this S back in here? How do we write that down? Well, let's try to write it this way because we used that trick earlier. F of S, right? F of this is a joint distribution of S and T. Numerically, they're the same. Numerically, they're the same. I'm using the discrete scenario because T is determined by S. These are the same. These two are the same, and what else? Let's write that as a how do we show this factorizes? Use the conditional formula, I guess. F of T S given T, S of S given TS times T, which might depend on theta. Actually, both might depend on theta. Where did we use this, huh? Where did we use this? Huh. I'm struggling to prove the converse of the factorization theorem because the forward direction is rather easy. The thing is, can we say
if you have sufficiency, do you have this factorized form? Actually, you know what? Because if you know T is sufficient, you must have the factorized form. Okay, guys, I'm going to AI, okay, and see how that turns out. Okay, so I'm going to AI a little bit. I'm going to use ChatGPT and see what we can get from ChatGPT. Okay, so here, let's see. Assuming T is a sufficient statistic, assuming T is sufficient statistic, can we actually, by that we mean, let's use, by that we mean if sufficient statistic, okay, T equals T of S, where S is a sample. By that we mean if whenever, so we're using the definition in the book. Whenever we have that, you just write the likelihood function L. You know what? Let's use the density, the joint MGF, joint not MGF, no joint PMF, f of theta given S1. Actually, that's not the how you write it, but f subscript theta of S1. It was theta S1 equals C of S1 S2 times f of theta times S2, where f of theta is the probability mass function, or just PMF of the sample. Okay, we're assuming discrete model. Okay, so here, can we show f theta factorizes? Okay, can we show that f theta factorizes, i.e. f of theta S equals h of S times g of theta? Because in the text we only prove the opposite direction. We assume the factorized form and prove T is sufficient. Can we do the opposite direction? That's the thing. Okay. The assumption. Suppose let S denote the sample space. Suppose T is this function, and you're assuming that whenever T of S1 equals T of S2, there exists constant C1 C of S1 S2, then this relates. This is exactly the likelihood ratio characterization of sufficiency. Okay. Choose a representative from each fiber. Fiber, I guess it means sample space. For each value, little t in T of S. Okay, so T of S, that's the range. T of S, that's the range of big T. You choose one representative sample. R depend on T and S. Right? Because the inverse function is generally speaking not, does not exist. The inverse image is not a singleton. So let's pick one. Okay, let's pick one such that T of our
RT is little t. So that's one representative. So it's like picking one data point from the equivalence class. The axiom of choice is unnecessary if the sample space is finite or uncountable. That's fine. Let's ignore that. Okay, so now let's define. Now let's define this is the function of t, because this is well defined. This is well defined. Well defined must mean the value does not depend on the choice r. Why? Why is that? Because RT is fixed. Why is this well defined now? F of theta, remember f of theta is the joint density of the sample. Here it says that R is only depend. Hang on a second. Why is this well defined? Here we wish to show this is independent of the representative. That's what well defined means. Oh, that's a bummer. I don't know why. Because here it's not clear, no? It's not clear. Or maybe this follows from sufficiency. So imagine you have, let's say, R is like a little s, basically. R is like a little s. So imagine you have two R's, okay, R1 and R2. R1 and R2 that come from the same equivalence class. Can you ask it to clarify? Yeah, I will. I'm just trying to figure this out myself first. But the sentence says RT is fixed. RT is fixed. I mean, you choose one RT is fixed, but that's nonsense. I mean, it's not nonsense, but the idea is this sentence, this is well defined, means what? Means the right-hand side is the same for all the representative sample R. Okay, given T, right? Given T, R can be many, right? Given T, R can be many. The point is the right-hand side only depends on T, does not depend on R. But right now it's not clear to me that's the case. Okay, so imagine this is R1. So imagine this is one representative sample R1. So F theta of R1 should be C R1 R2 F of theta R2. I don't know why this is independent of R. Okay, just leave it here. This is a huge jump in the logic. You just define T theta of T to be F of theta RT. Okay, then let's define H. What's H? For any sample S, let T equals big T of S. Okay? So this gives us, what on earth? It doesn't seem to mean that, but it only made a choice. Although there's, yeah, exactly. It's only made a choice. Okay, so let's keep going. So F theta of S I have zero clue of what is going on here. Oh, cat wants to play. So you see here, oh, okay, here use the definition of sufficiency. Yeah, which makes sense. And then it uses the fact that F theta of RT only depend on T. The converse is immediate, right? The converse we showed in the text. The converse somehow, right? The converse is the factorization theorem in the textbook, but somehow the opposite direction is not shown.
Very weird. Okay, guys, I'm looking at Casella and Berger. Okay, guys, I'm looking at Casella and Berger. Uh, I'm just going to read things, okay? I'm just going to read things. Well, let's finish this today because this is really bugging me. Because Casella and Berger and this book uses different notions of sufficiency. Okay, so let me just set it aside and do a separate treatment. Okay, and then see how these two fit together. Okay, I have Casella and Berger with me, but I cannot show the PDF because it's illegal. I'll just give the relevant information here. Perhaps I can perhaps this way I can stream future in the future books that are copyrighted. But there's a great catch because if I do that, I need to have prior knowledge. I need to have prior knowledge about the book. Casella and Berger is one that I'm relatively familiar with, if I do say so myself. For some unfamiliar book, I'm not sure how well will that go. But we can do an experimental stream to figure that out. So, okay. So in CNB, Casella and Berger, on page 272, this is the second edition. Okay, page 72, definition 6.2.1 says a statistic T of big X. So in Casella and Berger, big X stands for the sample. So in Casella and Berger, we use the bold font. So I'm just going to put a down arrow, a down bar here to represent the sample. The statistic Tx is sufficient. This is sufficient statistic for theta. If the conditional distribution of the sample x given the value of Tx does not depend on theta. So that's the definition of Kassan-Berger, which I put here as a proposition, because I'm more familiar with this version of the sufficiency, and I try to prove that it's equivalent to what is given in Evans and Rosenthal, but I wasn't successful. So here, this is a definition in Kassan-Berger, and there is a theorem that says this. So this is page 274 theorem. 2.2, theorem to 2.2. It says if P of little x given theta is the joint. Okay, the notation might be a little bit different compared to Evans and Rosenthal, so we'll just have to do some translation. So if this is a joint PDF or PMF, let's use PMF, okay? It's a joint PMF of X, works for PDF as well. And Q little t given theta is the PDF or PMF. Let's once again use the PMF. Is the PMF of big T. Okay, if you have those two, then big T is a sufficient statistic for theta. This is the big T is a sufficient statistic for theta if for every x, if let's say if p dot given theta divided by q q of t dot given theta is independent of theta. If this ratio is independent of theta. So this is a theorem. So as you can see, this is a sufficient condition for sufficient statistics. The conclusion is T is sufficient if this is independent of theta. Okay, so that's what is given in Casella and Berger. We'll look at its proof very shortly. But here we have the final result. This is on page 276. Theorem 6.2.6. 6.2.6, a factorization theorem, which for some reason the book by Evans and Rosenthal only contains one direction. In Casella and Berger, factorization is an if and only if statement. Okay, let little f of x given theta be the joint PMF of x, the sample x. Okay, T of x is sufficient for theta if and only if, okay, if and only if, this is important, if and only if you can write the joint PMF this way, gt of x, which given theta, times h of x, for some functions g of t given theta and h of t and h of x. Okay, so that's the logic here. That's the logic here. So we might need all of them. Okay, we might need all of them, but let's just see how this is proved. Okay, so let's first prove theorem 6.2.2. Okay, proof of theorem 6.2.2. Okay, in the textbook, however, it is written in a not very, so to say, a very formal way. Okay, so let me just try to give like an actual proof. Okay, in Casella and Berger, it says to understand definition 6.2.1, let t be a possible value of big T of x. We wish to consider the conditional probability of big X equals little x when big T equals little t. Okay, so you wish to consider the conditional probability. If x is a sample point, by the definition, if big T is a sufficient statistic, this conditional probability is the same for all values of theta. Yeah. A sufficient statistic captures all the information about theta in this sense. Consider experimenter 1. Okay, consider experimenter 1 who observes big X equals little x, and of course can compute the value of t. To make an inference about theta, he can use the information of the full sample or the value of big T. Now consider experimenter 2, who is not told the value of big X, right, but only the value of the sufficient statistic. The experimenter 2 knows the distribution of X given T. Suppose the experimenter 2 knows the conditional distribution of X given big T. Because experimenter must know, right? Must know because this can be computed from the model without knowing the true value of theta. Thus, experimenter 2 can use this information and a randomization device to generate an observation Y. To generate an observation Y, so that it follows the distribution, so that it follows the conditional distribution when t is fixed. It turns out that for each value of theta, x and y have the same unconditional distribution. Hold on a second. For each value of theta, x and y have the same unconditional probability distribution, as we shall see below. So experimenter 1 who knows x and experimenter 2 who knows big Y have equivalent information about theta. But surely the use of random number table to generate Y has not added to experimenter 2 knowledge of theta. All his knowledge of theta is contained in knowledge in the sufficient statistics. So experimenter 2 who only knows the sufficient statistic has just as much information about theta as does experimenter 1 who only knows the entire sample. Okay. Okay. So it turns out that's not super relevant. It's not super relevant, but basically let's prove theorem 2.2. Okay. If this is independent of theta, then you have sufficiency. Then you have sufficiency. So let's try to do that using the definition 6.2.1. Okay. So suppose P dot given theta over Q of T of dot given theta is independent of theta. Okay, it's independent of theta. So let's calculate this. Let's calculate in general the probability of big X equals little x such that big T of X equals little t of X. Okay. Okay, so here we have the definition P theta of the joint distribution, a joint probability divided by the probability of the condition all right. So well, if x equals little x,
then t of x must equal to t of little x. So here you have the first event implies the second, so you can just ignore that. Using the language of set theory, this says, okay, t of x equals t of little x. This is an event that contains x equals little x. If x is equal to little x, then t of x, of course, equals t of x. So here you're taking the joint event, so you can just ignore the bigger set and just keep the smaller one. Okay. So this is p theta of x equals little x on top. And at the bottom, oh no, this is not t, but what did I just wrote? This is nonsense. Probability of t of x bar equals t of big X bar equals t of little x bar. In general, both depend on t. Both depend on theta. And of course, by definition, upstairs is just p of x given theta. Downstairs is q of t of x, big T of x. Independent of theta. Okay? And this is independent of theta. So by definition, we're done. So by definition, 6.2.1, big T is sufficient. So this is immediate. Okay, so that's cool. And now let's turn to the proof of the second one. To the proof of the second one. The definition, the theorem called the factorization theorem. Okay, so the factorization theorem. So what we were struggling with was the reverse direction, right? Suppose T is sufficient, we want to show factorization holds. Okay, so this is proof of theorem 6.2.2. Okay, so let's assume T is sufficient. Need to show factorization. So how do we do that? Okay, so here it's let's try to first write down the joint density, probability mass function of the sample. So by definition, this is the probability of x equals little x. Potentially depend on theta. Typically depend on theta. And as we mentioned, you can just add and you change that to the joint event. Big T of x equals big T of little x. You can do that, assuming, well, no assumption needed. It's just that. Okay, and then use conditional probability. P of theta big T of big X equals big T of little x. marginal. That's the condition, and 10 times the conditional probability. And the conditional probability here, you can drop the subscript, no subscript here, because x given, no, sorry, not x, x equals little x given big T makes use of sufficiency. So this makes use of sufficiency. No theta here because of sufficiency. Definition 6.2.1. Okay, and now what we have here? And now what we have here? So let's write gt of theta to be probability of theta big T of big X equals little t. Okay, this is the marginal distribution of t, and h to be the rest, and we're done. So you do have factorization. This is almost immediate, huh? So therefore, f of x given theta is gt of x given theta, actually big T, times h of x as needed. So just to complete the proof, let's do the opposite direction. Let's assume you have this factorization. Assume factorization, you need to show t sufficient. Basically, you need to show the conditional distribution of x given t does not depend on theta. Okay, so how do we do that? Assuming factorization, first of all, let's try to express. Actually, you know what? Let's make use of 2.2. 2.2. So let's just try to express the ratio between here, the ratio between the joint PMF of x and the PMF of t. Okay, so let's do that. Yeah, so let's we make use of 2.2. Okay, so here the joint PMF over the marginal PMF of t. Okay. Here you use the factorization. On top you use the factorization, which is g of t of x given theta times h of x. Okay, over the same thing. Okay. And now what? Well, let's try to express the marginal. Let's try to express Q. So on top, everything stays the same. G of t of x given theta, and then times h of x. Well, at the bottom, you can think of it as the hang on. Um, how do I express Q with G and H and all of that? Well, Q is what? Q is, think of this Q. Q here, Q is the sum of fx theta, where, hang on, let me just use a different letter, y. You're summing over y such that t of y such that, okay, summing over y such that t of y equals t of x. Now you're summing over this equivalence class here. Okay, and now you can just use the factorization again. This time at the bottom. Y such that ty equals tx. Use the factorization again. So at the bottom you have t of x, t of y given theta times h of y. And on top, everything stays the same. Okay, so how does this work out? Well, because here you see in every term t of y is identical, is fixed to be just t of x. So you can do the substitution downstairs. So this is upstairs. Do the substitution downstairs, and you can substitute t of y to be t of x. And after you do that, this term, the first factor, has nothing to do with y anymore, and it can be taken out of the summation. So basically every single one of these terms is the same. So g of t of x given theta, and then you just sum over y such that t of y equals t of x, h of y. And of course, these two terms cancels out. You get h of x over the sum of h of y, where y, the summation takes place over the equivalence class, basically. And so that's finishes the proof. Right? So you use this ratio is independent of theta. You see, independent of theta. And then by 2.2, t is sufficient. Okay. So you do have both directions, basically. So you do have both directions. And now we wish to prove something else. Okay, now let's prove something else, proposition. So basically, we want to show this definition, theorem 2.1.1 is equivalent to Evans's definition. Okay, proposition. So T is sufficient if and only if whenever T of S1 equals T of S2, f of S1 given theta
f of s1 given theta is the same as c of s1, s2, f of s2 given theta. So if we can prove this proposition, then everything is safe. Okay, then everything is safe, and um, this difficulty does not need to be resolved. Okay, this difficulty does not need to be resolved. So let's use everything we used so far. Okay, so now see if we can show equivalence. So let's try to prove the opposite direction. Because to check sufficiency, we just need to verify. We just need to verify the assumption in 2.2. Okay, we just need to verify that the here the okay where okay proof is the statement is here. So just need to show that the joint distribution of x and the ratio between the joint distribution of x and the distribution of t does not depend on theta. Let's do it. Let's do it. Okay, so what is the joint distribution of t though? What's the distribution of t? So given is okay. So given f s1 theta, what is q? Remember, we want q t of x. What is that? Given theta. So how do we calculate that? Well, you can, like we did that earlier. So you can sum over given that. So sum over f of s given theta, the value of s such that t of s equals t of x. How do we prove that t is sufficient now? We wanted to verify the 6.2.2. We want to verify that the joint distribution of the sample and the marginal distribution of t does not depend on theta. Can we do that here? Here we have a ratio that is independent of theta, I see. This is quite nice. Remember what we want. We want f of x, okay, given theta over q of t of x given theta. We want this. Okay, on top let's write. Okay, on top let's write c of x s f of s given theta on top. Actually, I need to assume ts equals tx. then I can use this form f of s given theta. So now I have that. On top we have that. At the bottom, let's write the substitute. Let's substitute. Okay, sum s such that t of s equals t of x, fs of theta. Can we make some shenanigans happen? So perhaps let's write this as c of s given x, s and x, f of x. Can I write that? Of theta. Since I'm summing over x, this can be pulled out. Is that how it works? Yeah, actually, you know what? Let's do that. Actually, you know what? Let's do that. So here at the bottom, on top, everything stays the same. So what I'm trying to do is to reconcile the definitions in two textbooks, basically. Here you have, let's use, so now your S is the first position. Let's use X as the second position, C as X, f of X given theta. Now because summation is over S, f of X and theta can be pulled out. And the two cancels. Do you guys see that? F of X given, yeah, this just cancels out. In fact, there is not even a need to use the CX. You can just leave the f of x theta on top. Okay, so leave everything the same on top. Looks nicer actually. Yeah, so it's just 1 over the sum s such that ts equals tx csx. This is independent of theta. Okay, so therefore by theorem
6.2.2, T is sufficient. Okay, so that's one direction done. In the second direction, when you have sufficiency, well, this holds. Let's see that. And that's not difficult because we already proved that, right? Because once T is sufficient, by factorization, you have, well, factorization. So now you assume T is sufficient. You can use factorization. You're pretty much done. So by factorization, f of x given x, this is g of big T of x given theta times h of x. So you're pretty much done here. F of S1 given theta over f of S2 given theta is what? Is g of T of S1 given theta h of, assume T is sufficient, okay? Assume T is sufficient, h of x1, h of S1 g of S2 given theta h of S2. Okay, so if TS1 equals TS2, we need this. If TS1 equals TS2, then the ratio would have the G cancels out, and we're done. Okay, use the factorization theorem, this is done. And this is called that C of S1, S2. So we are done. We're completely done. Okay, so I think now we're very satisfied now. Okay, we're very satisfied. So we managed to prove all the equivalent characterizations of a sufficient statistic. So we have four. We have four equivalent characterizations. You can understand this concept in four ways. First, you have the conditional characterization. Conditioning on the sufficient statistic, the sample conditional distribution does not depend on the parameter. Second, the joint distribution of the sample, okay, the ratio between the joint distribution of the sample and the marginal distribution of the sufficient statistic is independent of theta. The second characterization. Third characterization is the celebrated factorization theorem. And the fourth one is the likelihood ratio characterization. Four characterization. How do you guys like that? Summary. Four equivalent characterization. Actually, you know what? You know what? We don't know about the converse of 2.2, huh? If T is a sufficient statistic, then it should be, right? They should be, because they're literally the same. They're literally the same. So, yeah. So that's equivalent. So theorem 2.2 is also a characterization. If you have T is a sufficient statistic, then this ratio is independent of theta. If you have this ratio independent of theta, then T is sufficient. Everything goes both ways. Okay, so we remark that this theorem is incomplete here. This is incomplete because I mean, it's not wrong, but it goes both ways. And in fact, there so many different ways to define it, of sufficiency. For equivalent characterization, 1, x given t follows distribution independent of theta. 2, the distribution function of x over the distribution function of t of x independent of theta. Third, factorization theorem. Okay, factorization of distribution function of x. Okay. Fourth, likelihood ratio characterization. Hang on, is that likelihood ratio? No, it's actually not the likelihood ratio. It's not the likelihood ratio. Right? Likelihood ratio refers to things like L of theta 1 over L of theta 2. Here, theta is the same. This is not likelihood ratio, but rather, let's just call that equivalent likelihood characterization. So basically, 4 says, same t-value if and only if equivalent likelihood. Okay, so that's 4 characterization. How do you guys like that? Okay, so I think we can safely call it a day when it comes to statistics. Because we started at 7, right? We started at 7. So if you guys, if you guys, you can leave at any point. But I think I wanted to I want to finish at 12. Okay, I wanted to another hour and 15 minutes. I want to do ballistics. Okay, I just want to use the bathroom real quick. I'll be back. All right, guys. Here we're going to discuss the basic equations that governs rigid motions. This is a completely different topic. 5-hour stream teaching math. Wow, here my professor can't even teach for an hour with an active learning approach. Well, I mean, in academia, teaching is more like a, let's just be honest, is more considered like a chore. Their main thing is to publish papers, right? So you gotta know the institutional incentive. If a professor is tenured, he has more incentive to spend more time on teaching. Like for me, you can call it teaching, but I guess it's just a matter. I mean, I do this on my own. Like I pretty much I do this on my own, and I'm just like live streaming the process. Like, so I'm just glad that even people are interested in watching this, because if nobody watched it, I would just do it on my own. It's a completely solitary endeavor. But now I'm just talking to a screen. That's the difference. And people apparently sometimes find that interesting. So thank you very much for that. All right, guys, let's start with something completely different. Here we have a set of particles, finite or infinite in number, will be called a body. What we call a body? A body is rigid if each pair of its particles keep the same distance apart at all times. So that's a rigid motion. It's a purely geometric notion, right? So there's no physics going on. It's just pure geometry. As it moves, every particle pairwise stays at the same distance. So thus, if x of t and y of t are the position of the vectors of two particles of the body in any coordinate system, we must have the distance being a constant. Let's draw a picture to illustrate what's going on here. So you have an arbitrary coordinate system. The coordinate system might even be moving. The coordinate system itself might even be moving, but it doesn't matter. Okay, let's here just draw a coordinate system that's fixed. In physics, they typically call it the lab frame. Lab frame. So here you have a blob of stuff, and after time t, okay, it moves to this position. So I mean, I hate. It's hard to draw the same shape in a different, because I just drew this arbitrarily. So let me just. Okay, so that's a different shape. No, that's a different position. Hang on. Can we move this? Okay. Yeah, let's just put it here and let's maybe turn this way. Okay, so that's the rigid motion. Actually, you know what? Let's put 2 points in there. Let's put 2 points in there. Delete that. Okay, let me put 2 points in there. And I think I might need to close off this one just to have more, so the computer runs faster. Yeah, ChatGPT takes a lot of memory. System theory. This is not system theory, it's just classical mechanics. System of particles, x and y. Okay, so now you have a body and you pick 2 arbitrary points and you're just going to shift that. No, not shift that, but apply a rigid motion to it. You can translate, it can rotate. In fact, that's a theorem. So basically it says, we will probably get to that. It says a rigid motion can be decomposed into a translation and a rotation. We'll see if that's included in the textbook. Okay. If not, I will probably end up making a video about it because it's such a nice application of linear algebra. Okay, x from the old position to the new position, and y from the old position to the new position. But the point is, the relative distance is the same at all time. So x of t minus y of t. Cat is very angry. I don't know why. They already had treat today. So this is constant for all t. We want that. Right, so that's the rigid motion. So I think a little bit of history. Euler pioneered the study of rigid motion. Euler, I think when he was in Prussia, and was given a task of doing research for naval construction, shipbuilding, or something like that. So basically, Frederick the Great tasked him a bunch of stuff that are perhaps useful for the economy and whatnot. And he developed the theory of rigid motion for shipbuilding. That's the main motivation. Okay, so which amounts to the same thing, that x minus y dot product with itself is constant, of course, because the length squared is the dot product with itself. Okay, so if x, y, and z are the positions of vectors of any 3 points, okay, so we want to have more identities. Let's try to deduce that. You just close off the Discord. Here, this is of course equivalent to xt minus yt dot product with itself is being a constant for all t. Okay, cool. And then what else? If x, y, and z are the positions of vectors of any 3 points in a rigid body, then we can subtract and add z basically, and expand. So let x, y, and z, which are depend on t, be functions of t in a rigid body, or of a rigid body. A rigid body is a collection of points. And we're not even assigning masses yet, right? Because this is purely kinematics. This is purely kinematics, not dynamics. Just the geometry of motion. Okay, x minus y length squared is what? You can write it as x minus z minus y minus z length squared. And this gives you what? Gives you x minus z minus y minus z together, taking the dot product with x minus z minus y minus z. Okay, and then you expand that, you get x minus z length squared, dot product with itself basically, and you should have cross terms minus 2x minus z using the symmetry of dot product, y minus z. Right now I'm still not sure where this is going, but let's just keep following. Okay, so this is certainly true. Along with 7, what is 7? Well, 7, as we said, is for any 2 points. For any 2 points, the relevant distance is the same. So here we can see that. Okay, here we can see that x minus y squared is a constant. X minus y length squared is constant. X minus z length squared is constant. Y minus z length squared is constant. So overall, you can isolate the middle term, the cross dot product term. Not the cross term, that's nonsense, but basically the term in the middle. Okay, so just isolate that. X minus z dot with y minus z. Can isolate that, and it looks like 1/2 of x minus z length squared minus, or plus, okay, plus y minus z length squared minus x minus y length squared. So this is a constant. This is a constant. This is a constant, and by differentiation, this yields the useful identity. Okay, so how do you differentiate? By differentiation, we don't want to break the bracket apart. Okay, so differentiation. Let's use a vector identity. So the upshot is a product rule works for dot product. The product rule. So if you have AT and BT are vectors, then the derivative of the dot product works very much like the ordinary dot product for scalar value random variable. Oh, it's not random variable, my goodness, variables, okay, functions. Okay. Plus AT dot with d over dt bt. So the product rule works for dot product as well. Okay, so now you have a dot product equals to a constant, and then you can differentiate. Let's call this star, differentiate star, d over dt. Let's use the dot notation, the Newton's fluxion notation for the derivative. So you get d over dt, x minus z, these are all vectors by the way, or y minus z equals 0. By the product rule, this is x dot minus z dot times y minus z plus x minus z times y dot minus z dot equals 0. Equals 0. So here, move the terms. Okay, so we don't know still. I still don't know why this is useful, but let's just follow along. Okay, so dot product. Everything still is dot product. Y dot minus z dot. Okay, so cool. So we have that. This is true for all t. Okay, assuming the function is differentiable and whatnot. Okay, and this is true for every 3 particles of a rigid body, provided of course that x dot, y dot, and z dot are well defined. In particular, if y and x are the same. Okay. If y and x are the same, well, if y and x are the same, then both sides, okay, if y and x are the same, then you simply get x dot minus z dot quantity dot product with x minus z equals to its own additive inverse, so it must equal 0. So this tells us a perpendicularity relation. Okay, so 11 is a perpendicularity relation. So let's do that real quick. So set y equals x. You get x dot minus y minus z dot product with x minus z equals 0, because it's equal to its own additive inverse. So this means x dot minus z dot is perpendicular to x minus z. So x dot minus z dot, this is first of all, x minus z, this is the relative distance. Right? This is a relative distance. The relative distance, and here you have the relative velocity. The relative distance is always orthogonal to the relative velocity to ensure the length stays constant. Okay, so that's pretty cool. Let's keep reading. In a later theorem of this section, we shall wish to choose 4 points of a rigid body with position vectors x0, x1, x2, x3 such that x1 minus x0, x2 minus x0, and x3 minus x0 are mutually perpendicular unit vectors. Clearly, this may be impossible, for example, when the body is contained in a sphere with diameter less than 1, or when the body contains less than 4 points. However, these cases offer no real difficulty, for we can show that an axis can be attached to a rigid body. Okay, so basically you want to attach a moving frame. Right? So that's the, you want to attach a moving frame to a rigid body, and this is always doable. Okay. Anyway, that is, it is possible to define a coordinate system in such a way that every point of the body has a constant coordinate in that system. So that's the fixed, not the fixed, but the moving frame. The moving frame that is attached to the rigid body. Okay, and from that frame, every point in the body have constant coordinate. Okay. And B, every 2 point with constant coordinates in the system keeps in the system, the same system in A. Okay, every 2 points is constant coordinates in the system keeps a constant distance apart. Yeah, makes sense. Thus, by B, all the points with constant coordinates can be thought of as the particle of a rigid body extending throughout space, and by A, this extended rigid body contains one we started with. Sure. So the idea is it is possible to define a coordinate system that is fixed to the body. Okay. Thus, by B, here we already have that. In order to avoid some mathematical complexities, we shall disregard the case in which all the particles of the body lie on a line, and we shall prove. Okay, so this is very rigorous. You see, it's very careful about all these corner cases. But anyway, let's first ignore. I don't know why we ignored the case, but perhaps it will become apparent later. Here it says we discard the case in which all the particles of the body lie on a line, and we shall prove a lemma. And if we shall prove a lemma, 12. Let B be a rigid body contain at least 3 non-collinear particles. So imagine a triangle. So at least it contains a triangle. Then there exists a coordinate system having property of 1 and 2, A and B, of the preceding paragraph. Okay. So you want to construct I think this shows the lemma is there for proof. Okay, I think it's fair to ignore this lemma, right? We can just take it for granted, right? Let's take it for granted because the whole point is that if it contains at least 3 non-collinear particles, right, then you can avoid, right? You can avoid the situation where all particles lies on the line. And once that is avoided, you can construct the coordinate system as you wished. Okay. So anyway, let's ignore this proof because I think this is intuitive enough. Unless later on we have some issue, and we'll come back. So with respect to the given coordinate system, a given coordinate system, I think this is not necessarily a fixed or a moving coordinate system, just an arbitrary coordinate system. With respect to a given coordinate system, the motion of a rigid body at an instance t0 is a translation. If at an instance, if all particles of the body have the same velocity. Okay, so that's the definition of a translation. It is defined as instantaneously. I'm back. I had to code up a machine learning pipeline. I had to apply measures here to some. Now I'm trying. Well, thank you very much. Well, I mean, no, thank you very. But that's really awesome, right, Sha? That's thank you. First of all, thank you very much for coming back, and well done. Okay, so just to recap what we just did. Okay, we finished the discussion on sufficiency and summarized 4 equivalent characterizations. 4 equivalent characterizations of sufficiency, which is, in my opinion, pretty cool. And now we are deriving the kinematic relations for rigid motion. This is for ballistics. Just to give an idea where we're going, of course, this is rather general. Right? The notion of rigid motion is rather general. It's an application in linear algebra. But as a practical application, you wish to study the stability of a shell. Right. So typically, shell has some sort of rifling. So a projectile spins. The spinning is to minimize precession. So this is a typical precession. So a shell during its flight may have its axis rotate about the trajectory of the center of mass. Of course, this is a source of instability. We want to minimize that. But such behavior needs to be studied. And of course, to study that, you cannot treat the projectile as a point mass anymore. It has to be treated as a rigid body. So here we're starting from the fundamentals of rigid body motion. Okay. So yeah, that's the. By the way, this textbook is called Exterior Ballistics by McShane, Kelly, and Reno, written after World War II. So I think this is the end of Korean War. These three fellows worked for the U.S. government during World War II. McShane is a real analyst. Um, McShane is a real analyst, and also wrote book on stochastic calculus. Kelly is a topologist. Reno is an applied mathematician dedicated to weapon manufacturing and design, but it turned out he was a Soviet spy. Reno was a Soviet spy, and he was given time to finish this book before being put into federal prison. So that's kind of interesting. Shah says rigid body have really deep connection with some representation. Yes, yeah, exactly. So rigid body is extremely deep. I think it's totally possible to start a separate course on the mathematics of rigid body. Yeah. Okay. So yeah, this is a very interesting book, and it's highly mathematical, even though the subject matter is highly applied. Law to what? To the Russian spy? Yeah. So if you guys know some military history, um, the Allies, the Western Allies, the Americans and British conducted high-level bombing campaigns against the Nazi Germany, right? So they have the heavy bombers, B-17s and Lancaster, I believe, Avro and Lancaster. I mean, how did you write so nicely with just a mouse of one? It's impossible for me. I guess it's just a practice. I guess. Is this nice? It looks very much chicken scratch. but I mean, I'm trying to write things fast. That's the reason, right? I didn't try to uh, write things super nicely. It's just enough for me to to look at the letters and not be confused. So, anyway, I was talking about there's something called the Northern Bomb Sight. The Americans and the British, in particular the American, I don't know much about British, but the Americans have something called the Northern Bomb Sight. Yeah, so this is a device. Of course, bombing during World War II is horrendously inaccurate. Northern Bomb Sight um, this was used in the U.S. Army Air Force, blah blah blah. So this was developed during World War II. Okay, and I believe Reno played a major role in it. Can we search it up? Reno. No, it's not here. But yeah, so if we check, for example, the Franklin Reno, yeah, Franklin Vincent Reno, he was a communist and was uh, recruited by the GRU, the Soviet military intelligence agency. Okay, so this is what he did. Reno graduated from University of Colorado Boulder with top honors in mathematics. While doing grad study in astronomy in University of Virginia, he joined the Communist Party under the name Lance Clark. Yeah, he worked on the Northern Bomb Sight and was said to have passed information of this device to Agler His. This is another Russian spy. In 1952, he pleaded guilty not to disclosing his Communist Party when he was being screened for the Aberdeen job. He was sentenced to 3 years in federal prison. It's actually pretty lenient, huh? I think. And guess what happened if you spied for the American on the Russian side? let's say if you're a Russian scientist and it turns out that you're found out that you gave information to the Americans, can you imagine what will happen to you? The Soviet had two hobbies: espionage and probability theory. Well, the Soviets have their own top-tier physicist and mathematician. Of course, espionage helped, but it's not like I mean, it certainly accelerated their military research and whatnot, but they have their own top-tier scientists. Reno also collaborated with McShane and Kelly, called the book on exterior ballistic. The judge gave Reno a month's delay in reporting for his sentence so he could finish his work on the book. Right. Yeah. Consider what he done. He had a pretty good life. Yeah. If he is a Russian and was discovered that he communicated with the Americans or any other country, he would be dead. He would be stone dead. Right. Anyway, going back. I decided to skip one lemma. Hopefully this won't bite me in the butt later on. I just want to get to the main theorem. Okay, so where we're going here. And nonlinear reading is quite common. You don't feel terribly bad about it. So the definitional translation. At any instance, at one instance t naught, the motion is said to be a translation. If all the particles have the same velocity, the equation x dot equals y dot at t naught holds for positions x and y for every pair of the particle of the body. The motion at time t naught is said to be a rotation. Okay, the definition of rotation. What's the definition of rotation? Rotation, how theoretical is this book? It's very theoretical. It looks like applied mechanics, but as far as this subject is concerned, it's highly theoretical because everything is. Just take a look at the content. As far as the subject matter is concerned, it's highly theoretical. Chapter 1, Mechanics, Dimension Analysis, and Statistics. These are like the prerequisite. Now, so we're still in the prerequisite section. Force system of a projectile. Gravitational Coriolis forces, aerodynamic forces, some fluid mechanics, method of measurements and whatnot, the normal equations. So these are the differential equations that's needed to calculate things like range table. Approximation method, including the famous Ciassi method, invented by Italian before World War II, before World War I, actually. Numerical integration, differential correction, various little disturbance that affects the trajectory, differential effects and weighing factors, method of computing differential corrections. So these are, I don't know how many of them are actually still currently being used in a military setting, but these numerical techniques are certainly spilled over to other domains. My research group office used to belong to applied mathematics. Left some old typewritten book, real complex analysis, ODE, nonlinear, all that good stuff. Yeah. So, yeah. As if you can, because these books are written by mathematicians. Once again, if you regular books, the most books written by McShane are on real analysis and stochastic analysis. And Kelly was a topologist. So you can clearly see the style, a lemma, theorem, and proof, and whatnot. Okay, so this is highly, pretty much follows the mathematical style, even though the subject matter probably belongs to engineering more than mathematics. Okay, the mathematical foundation is still here. If you're still here, if you guys are interested in a modern treatment. Unfortunately, I cannot live stream that book for obvious reason. But there's another book
called Modern Exterior Ballistics by Robert McCoy. By Robert McCoy, let me just do that, search that, and put that in chat. Robert McCoy, Modern Exterior Ballistics. So yeah, this is a book. You can see there's a PDF link, but I won't click it. And that's the cover. The launch and flight of dynamics of symmetric projectiles. So it's it quotes a lot of the theoretical derivations in the McShane book. Okay. So some of the derivations are skipped in this book are referred to this one. So as you can see, the mathematical foundation stays largely intact. Okay. And so let's continue. Okay. Let's continue here. Definitional rotation. The motion at any time at time t naught is a rotation about a point p naught. About a point p naught. So that's the center of rotation, huh? If p naught being rigidly attached to the body has okay, so p naught does not have to be a physical point, right? It can be treated as a point attached to the body. Here. You can consider a point being attached to the body. Then P naught has zero velocity. Okay, so let's put that down. The two classes of motion. I think where we're going is every motion of a rigid body. Yeah, it is easy to prove the following theorem. Every motion of a rigid body can be regarded as the sum of a translation and a rotation about an arbitrarily selected point attached to the body. So that's what we're trying to get to. Okay, so this is actually a purely linear algebraic result. Okay, I think I will probably end up making a video about it because it's such a nice application that is rarely mentioned in any book. It's not in Axler as far as I know. It's not in Axler as far as I know, and it's not in Gilbert's Strang either. Okay. So here, definition. At an instance, time basically, at an instance t naught, the rigid body motion is one, a translation, the translation if for all pairs x and y of bodies of body point x dot equals y dot. Okay, so that's the definition of translation. The second, a rotation, if there exists p naught attached to the body point. Okay, there exists a point p naught attached to the body so that p naught has zero velocity. Okay, definition. And now let's prove something. Here it says every rigid motion can be decomposed, right? Can be
regarded as the sum of a translation and a rotation about an arbitrarily selected point attached to the body. Okay, so here, okay, so let's take a look at this theorem. Let all x1, x3, x1, x2, x3 be the chosen reference system with coordinate vectors k1, k2, k3. Okay, and let x naught t be the position vector of any arbitrarily selected point p naught rigidly attached to the body. Okay, and let the star coordinates be a new coordinate system with origin at p naught, but with the same coordinate vectors, k1, k2, k3 as the original system. Okay, so let's draw a little picture here. I don't know why there's no picture in the book. Everything is described verbally. Okay, first let's copy down the statement. Every motion of a rigid body I think rigid body motion would make a good introduction to baby Lee theory. Just started with 3D rotation. And you prove the exponential of basically the angular velocity is the rotation matrix. That should be cool. Can be regarded as the sum of a translation, a vector sum, of course, and a rotation about an arbitrarily selected point attached to the body. So what are we doing here? So we have our original coordinate system. Oh, x1, x2, x3. Okay, so this is the original body. Right, and so imagine this is x naught t. The path x naught t. Okay. X naught t be the position of a vector of an arbitrarily selected point p naught rigidly attached to the body. Sure. Okay. So this is p naught rigidly attached to the body. Let the star coordinates be the new coordinate system with origin at p naught, but with the same coordinate vectors k1, k2, k3 with the original. Okay, so that means use a different color. x3 star, x1 star, and x2 star. So how do we go about proving that?
The directions are all the same because the coordinate vectors are the same. If a point P is fixed with respect to the new system, okay, P is fixed with respect to a new system, having constant position vector y, its position vector relative to, okay, so basically that's the relation. So here you have a point P with constant position in the new coordinate system y. And the old position, not the old position, but P naught has a position vector of x naught of t. So that means the position of P with respect to the original system, of course, is x naught t plus y, vector addition. So its velocity with respect to the original system is x naught dot. Right? Y is a constant, so it cancels out. And this is the same for all points P. It's the same for all points. So at every time the motion of the new system with respect to the original system is a translation. Okay, so here P naught is arbitrary. So P naught here is treated arbitrary. So if you consider that fact, and now you choose a special P naught, the motion of the body with respect to the new system is a rotation. Because P naught has zero velocity. Using the definition, P naught has zero velocity. Hang on a second. Where did we use the definition of rigid motion though? The motion of the body with respect to is a rotation, since P naught of the body remains fixed in the new system. Where did we use the hypothesis that the motion is rigid though? Is it because P and P naught stays constant distance? I wonder if this can be recasted into formal linear algebraic language though. I hope that's the case. It should be. It should be, because this way you can, if you're done that way, so if everything is purely linear algebraic, then you can see what assumption is being used where. Okay, so I think I might have to come back to this and do a linear algebraic proof. This is a more verbal proof, which I'm not super convinced actually. Okay, here you have a next result. Actually, you know what? We'll see. We'll try to prove this theorem on our own because this is quite important. Every motion of a rigid body can be decomposed into two parts. If we can prove that on our own, using nothing but linear algebra, I think that will be a success. But here, the next result is of great importance in the study of motions of rigid body. Because basically you want time derivatives. Theorem: let B be a rigid body, and O x1, x2, x3 a coordinate system. Then at each time t naught there is a vector omega. Okay, there existence of angular velocity. Exists a vector omega called the angular velocity of the body B with respect to the coordinate system x1, x2, x3. So this is a coordinate system. There's the theorem 16 does sound like it be, yeah, this is what I was talking about, right? Theorem 16 should be a purely linear algebraic result. right? And we shall prove it as such, right? Without many words, hopefully. So um, I think perhaps we can just take theorem 16 as given, and then look at 17, okay, 17 and 18. Okay, so here we have, I was saying that B is a rigid body and OX1, X2, X3 is a coordinate system. Then at each time t0, there is a vector omega called the angular velocity of the body B with respect to the coordinate system OX1, X2, X3. It didn't say whether the coordinate system is moving, is it attached, probably not attached to the body, right? It's probably just a fixed one. It didn't say, okay, it didn't say. Okay, that's okay. Such that the position vectors, okay, xt and x naught t of any two particles of B satisfies this equation. Okay, so it satisfies the relative velocity. Okay, the relative velocity between two particles is omega cross that, the relative distance. And the omega is the same. Remember, omega should be the same for all pairs of particles. This is the instantaneous, remember, omega can depend on t. This is the instantaneous angular velocity. See, angular velocity vector, the existence of angular velocity vector is by no means trivial. Okay, first of all, rotation on its own is not a vector quantity. Even though it might, you might think, oh, rotation requires an axis rotation and a quantity of rotation. Right? So you have a, seems like you have a direction and you have a size, right? And you can maybe use the right hand rule to fix a direction. Okay, now you have a complete direction, not just a line. You might be tempted to call that a vector, but it turns out it doesn't work because 3D rotation is not commutative. And vector addition must be commutative. So angular velocity can be added, but generally speaking, rotation matrices cannot. Right? Rotation matrices cannot be added and get another rotation matrix. It doesn't work that way. Rotation matrices, they form the special orthogonal group SO3. It's a group structure, it's not a vector space. But angular velocities, they live in a vector space. So that's the existence of angular velocity being a vector is totally non-trivial. Okay, so that's the statement. Here we have a proof of a modification of one suggested by A.P. Morse. This is a famous person. You guys probably heard of Morse theory, huh? Morse theory. He also worked during World War II on national defense matter. Is that? No, it's Martin Morse, not A.P. Morse, okay? Oh, different person, okay? That's a different, not the same guy from Morse here. But who is A.P. Morse? Let me just search that up. Who's A.P. Morse? Anthony Morse. Anthony Morse. A different person, okay? That's a different person. Oh, he's known as different Morse, but he worked with Kelly. Once again, Kelly worked. This is one of the authors of the ballistic book. Should not be confused. Yeah, it's a different person. I just confused it. Okay. After 2 years at the Institute of Advanced Study, he joined the mathematical faculty in Berkeley, where, except for the 2 interruptions, he worked for the rest of his life on mathematics. The first interruption is World War II. Worked at the Ballistics at Aberdeen Proving Ground. Time for me to go. I'll see you in the next stream. Thank you very much, Shah. Thanks for joining the stream. Yeah. So this is A.P. Morse. He's a topologist and set theorist. Okay. Apparently, his life was interrupted by the McCarthy's loyalist oath controversy. So yeah, that was during the Red Scares in during the state. Yeah. So like witch hunt against left-leaning individuals. Anyway, so here, this is a proof by AP Morse. AP Morse. Let x naught be the position vector of an arbitrary point p naught of the body. Arbitrary point p naught of the body. Oh, got it. And let us choose 3 points p1, p2, p3 rigidly attached to the body, so located that the 3 vectors each have length 1 and form a right angle orthogonal system. Okay, so now you constructed a fixed frame to the body. A body fixed to the frame. Okay, no, what the hell? A frame fixed to the body. Right, so this is the coordinate vectors, unit vectors. We denote the position vectors of p1, p2, p3 be x1, x2, x3 respectively. And for notational convenience, we define, okay, that's y1. Remember, the position vectors, this is probably relevant, related with respect to the fixed frame. This is probably with respect to the fixed frame. But basically, if you take the difference, y1 equals x1 minus x0, y2 equals x2 minus x0, y3 equals y3 minus x0, this forms an orthonormal basis, right-hand rule. And by the definition of vector product, right, that's the usual vector product relation between right-handed, a positively oriented orthogonal basis. Okay, so now you can do what? You can do the basics expansion, basically. Do the basic expansion. Is there any appeal to theorem 16 nodes? Because I was thinking about, is 16 important for 17? And you just do basic expansion and do differentiation. Where is 16 used? It's unclear, huh? Okay, so it's not clear from the first glance where the first result is used. Okay, I don't know where this is used. I don't know where 16 is used. But perhaps we can continue with the proof for 17. Okay, so we managed to describe a coordinate system fixed to the rigid body. Since y's are linearly independent, any vector z whatever can be expressed as a linear combination. Yeah, that's totally correct. But the yi are orthogonal and have length 1. Right, so this way you can easily find the coordinate by taking the dot product. Right, z dot with yi gives you the component ri. In other words, we have shown if y1, y2, y3 are 3 mutually perpendicular unit vectors, an arbitrary vector z satisfies the equation. Yeah, this is totally expected. As we shall first show that there can be at most one vector, at most. Okay, so this is uniqueness. One vector omega with which 18 holds. 18 is this equation. Angular velocity is unique, right? This is uniqueness means at most once, but then we have to show existence. We shall first show that there can be at most one omega with which 18 is satisfied, and we shall find an expression for this one possible vector. Okay, so to show uniqueness, what do we do? By 20, what's 20? 20 is the relation between
the cross product relation between the basis vectors y1, y2, y3. By 20, 5.16, what's 5.16? 5.16, that's the previous section, huh? 5.16. Here, rigid body motion is section 7. 5.6, what's 5.16? Let's go back. Probably a differentiation formula, 5.16. Let's come back to section 5. Oh, so that's the triple product formula. 5.16 is a triple product formula. I think everybody's seen it. Okay, so 5.16 is a triple product formula. What do we have? Well, of course, we will rewrite this proof ourselves because it's quite important. The existence and uniqueness of angular velocity. All right, so what do we have here? Okay, so let's consider the dot product between omega and y1. Right? Let's suppose omega exists and we want to show this it is unique. Right? Suppose omega exists. Let's take the dot product between omega and y1. Omega y1, omega dot with y1 equals omega dot with y2 cross y3, and then use the triple product identity. Okay, triple product identity, and then, oh, here, this step, omega cross y2. Omega cross y2 is supposed to be by 18. By 18. So suppose 18 exists, right? 18 can hold, you get y2 dot. Okay, so you get y2 dot here. y2 dot times y3. And in a similar manner, you can show that omega dot y2 is y3 dot y1. And omega dot y3 is y1 dot y2. Okay, sounds good. And what's omega? Well, omega, remember, you can let omega to be z in 22. Let omega be in z to 22, and then all the components are now specified. All the components, omega, using this expansion, and you get omega is y2 dot product with y3 times y1 plus y3 dot product with y1 times y2 plus y1 dot product with y2 and then y3. And this is the only possible vectors. And this is the only possible vector with which 18 can be true. So it remains to show that 18 does hold with particular omega. So you assume 18 hold and you get an expression of omega in terms of y1, y2, y3 and their derivatives. So there's that. But then you need to show this actually satisfies 18. Here we assumed 18. Here we assume, because this step, omega cross y2 equals y2 dot, this assumes 18. This assumes 18 here. So we need to show this expression actually satisfies 18. So it's just going to be a giant verification, I suppose. Okay, so we first make a preliminary calculation, namely compute y omega cross y1. Hang on a second, omega cross y1 is... Oh, you mean this expression cross y1, huh? By referring to the form of 25 over omega, we have this. We have from 20. What's 20? Okay, oh, this is the relation among y1, y2, y3. So, okay. Omega cross y1. Omega cross y1 is, first of all, the first term cancel because y1 cross y1 is always 0. And well, y2 cross y1 is minus y3. y3 cross y1 is y2. Okay, so cool. On the other hand, from 10, that's differentiation formula. That's a differentiation formula because, as we mentioned, y1 and y3 have constant length, remember? Constant length and constant angle. So the constant inner product. y1 and y3, the inner product is 0. So this is the result you get by differentiation and use the product rule. So you can rewrite the first term, the first factor, minus y3 dot with y1, minus y3 dot with y1 as simply y1 dot y3. Yeah? Hold on a second. Yeah, that's correct. So you put the coefficient for y3 into y1 dot y3. This is correct. And the second term, the y2 term doesn't change. There's a y1 term missing here, but that's okay. We can simply write 0 times y1 and replace 0 by y1 dot y1. This is rather ingenious. But basically, what we're trying to do here, so you see each term now looks like the following. So in the first position, there's a y1 dot, y1 dot, y1 dot. Perhaps this is intentional. Let's keep going. As been shown above in 22. That's a coordinate expansion. So on the right hand side, this is a coordinate expansion of y1 dot. This is y1 dot. And similarly, you can apply the same argument for y2, y3. So you get, basically that's omega cross y2 equals y2 dot. Omega cross y3 equals y3 dot. So you get omega cross yi equals yi dot for I equals 1, 2, 3. And now let x be the position vector of an arbitrarily chosen point rigidly attached to the body. Right? Okay. And so this way you can do the basics expansion once again. The difference vector x and x naught can be expanded in the y1, y2, y3 coordinate. And then you differentiate. By lemma 12, the numbers ai are constant. Yeah, exactly, because here y1, y2, y3 are vectors attached to the body. Are vectors attached to the body. So due to the nature of rigid motion, the relative position xt minus x naught t will have constant coordinate with respect to the frame rigidly attached to the body. Okay, so you just need to differentiate the basis vector essentially, and then you get the cross product relation. So you're done. Okay. And let me just finish reading the rest of the section. Can we do that? Actually, I cannot. You know what? I don't want to rush it. Let's just call it off of today's stream. And I'll see you guys next time. Next up is Tuesday measure theory. Okay. How many people are still watching, by the way? Probably not a whole lot because the chat has been real quiet. Okay, there are still 9 people watching. That's crazy. Thank you very much, guys. And I'll see you next time.